Hi, everybody. Welcome to the 2025 SPS Internship Program. We are so excited to have you all here. To start off, I did want to welcome Alejandro de la Puente, our Director of SPS and Student Engagement, to say a few words.
Yeah, thanks, Michaela. And I'm sorry for not being able to be there. I just want to take this opportunity quickly, obviously, to congratulate every intern that we have, but I just want to recognize the team, the SPS team, for actually taking this from beginning to end, especially for Michaela's contribution for kind of leading all the programmatic elements of this program. And obviously for Kayla Stevens for her guidance and support. Obviously the entire team as well for supporting all the interns during their 10 weeks in DC. And so that's all I want to say. So we have a great team, and I hope that you were able to really take advantage of this 10-week opportunity, and never forget that SPS and AIP are there to provide a lifelong connection to the physical sciences and to this community. And with that said, I want to throw in a line from a popular book. So may the odds be forever in your favor. And I believe that odds are a function of opportunity, preparation, and what you value. So take that into account when you're looking for your next steps. What do you value? How much are you prepared? And what is the opportunity out there? And then you will see things come together for you. So congratulations, and thanks, Michaela. I'll kick it back to you.
All right, there we go. Let me make sure that this is on.
Wait, I'll introduce you, MJ.
Oh, okay, good.
Okay.
Is the mic
All
on?
right.
Is the mic working?
I know you're excited to get started, but as our first presenter, I would like to give a round of applause to MJ, who is also not her first time around. She is a second-time intern. So give her a round of applause for one being our first presenter, and as well as her internship at Space Telescope. So.
All right, good morning, y'all. As Kayla said, my name is Mia Keller. I usually go by MJ. I graduated the University of Rochester this spring with a degree in physics and astronomy, and I was this summer Space Telescope Science Institute intern working on star formation rate calculations in Alpine C2 selected galaxies, which I will tell you about what all of those words mean in a couple seconds. There we go. First of all, even though I was working at the Space Telescope Science Institute, I wasn't actually working with any space telescope. So the most popular space telescope that's been in the news lately is the James Webb Space Telescope, located around Lagrange Point 2. It is in space, it is not here on the ground, and it works in ranges of the near to mid-infrared, which are wavelengths on the order of micrometers. I worked with the data from the Atacama Large Millimeter Submillimeter Array, which is at the Atacama Desert in Chile, here on Earth, down in South America, and it is what's known as a ground-based interferometer. So it's a network of 66 radio telescopes that are placed different distances apart from one another to create one super telescope that can observe in a much better resolution than any single telescope alone. ALMA uses what's called far infrared observations spread across 10 different bands that each use a different instrument to observe very narrow bands of wavelengths very, very precisely. So down there you can see a picture of the Atacama Array. Those are just some of the 66 telescopes, and James Webb up in space. That is a mock-up, not a real picture of it. One of the ways that we work with data from both James Webb Space Telescope and ALMA is using what's called spectral energy distribution fitting. We receive data from the telescopes in the form of intensities, what we see on the y-axis there, versus the wavelength that they occur at. So this is a little bit older of an image. Those are some of the different surveys that have been done, as well as the gaps that JWST and ALMA filled in. Because things like galaxies have very precise spectral energy distributions that we have observed over the years and know very well, we can fit data that we receive from these telescopes to pre-existing distributions based on models and use that to make inferences about what's happening in the galaxies. We can use SED fitting to discover star formation rate, mass, things like mass outflows, and the makeup of the gas in these galaxies. But all of this is heavily model dependent. So the more complete your data set, the better your SED fitting will be, but it still depends on the model that you're working with. ALMA telescopes can be used for both individual smaller programs and what are called ALMA large programs that dedicate tens of hours to on-sky observations that are designed to kind of build out the data set that we have on certain regions of the sky or certain types of galaxies. I looked at 3 different ALMA large programs this summer in ascending order of redshift, I looked at aspects, which covers galaxies from the local universe out to a redshift of about 4 over the Hubble Ultra Deep Field, which is that square image with tons of galaxies on it that you've definitely seen in the media. I looked at Alpine, which targeted 118 galaxies at redshifts between 4 and 6, specifically focusing on one type of emission from them. And I looked at the Rebels survey, which goes back even further from a redshift of about 6 to as far as they can see, looking for galaxies that they didn't know for sure how far away they were. Let me give you a little context on where those fall in the history of the universe. We are over here at the present day. Aspects goes from the present day back to a distance of about 4 redshift-wise. Alpine covers 4 to 6, and Rebels goes even further. Overall, I selected to work with Alpine data because I thought that it was both the most reasonable data set to work with over just the summer's timeline and a very interesting redshift range to get to study. Alpine data uses specifically ALMA Band 7 data. Band 7 at this redshift covers what is known as the C2 emission line. So based on electromagnetic emission, different wavelength peaks are redshifted or moved along the electromagnetic spectrum based on their distance from us to fall within different emission regions. So band 7 for the redshift range from 4 to 6 covers the C2 emission line. C2 is a very bright, very versatile emission line that can describe all sorts of wonderful things. Most importantly for me this summer, it described things like the star formation rate, as well as gas dynamics that are usually obscured by things like dust. Overall, Alpine found C2 emission in 75 of their 118 galaxies and set what are known as upper limits for the other galaxies in their sample. I chose to focus on galaxies that had secure observations of C2 rather than including upper limits like most of the literature has done so far. When looking at my Alpine data, I started with there are 2 different ways that they derive the star formation rate. One using spectral energy density fitting, like we talked about earlier, where we get 2 very normal-looking relationships. The one on the left is known as the main sequence, where we're plotting mass versus star formation rate. You can see it's nicely linear. And the one on the right plotting star formation rate versus C2 emission. Again, all of those lines in the background are nicely linear. Those are coming from the literature, and that black dashed line is what my research this summer showed. I also looked at what's a more standard representation of the star formation rate using hydrogen alpha, as we tend to do in the local universe, and found that it didn't line up too well. That opened up a lot of questions for me and my mentor because this line over here is the line of best fit. You're reading that correctly. So we took time following discovering that this is completely disagreeing data to consider how these 2 could be being confounded by variables that are in the sample. So this is the 2 of them next to each other for you to compare with the line of best fit for each of them plotted on each. And here are some of the other variables we considered. This is stellar mass. On this side, you can see we have a nice clear gradient going left to right, so we know that that's tracing mass correctly, whereas on this side, it definitely isn't. We checked to see if the UV emission had any bearing on it. Scrambled data, no clear bearing. What about the age of the galaxies? Once again, a little bit scrambled, no clear bearing. But when we got to looking at what's called the color excess, or the dustiness of the galaxy, we see over here in our hydrogen alpha emission, a nice clear gradient showing that there is some sort of correlation there, and using another measure that also traces dustiness, saw yet another nice clear gradient in our other variable. So we're feeling that the dustiness of these galaxies is definitely in some way impacting how our star formation rate is being calculated from these different variables. Overall, outcome-wise, that disagreement was not what we were expecting to see, and I was really excited to find it because it meant that I was doing something right and looking at something that hadn't been seen before. It brings into question some of these literature relations as well as their functionality at a higher redshift. That'll be exciting to look at in the future, but we didn't have time this summer. As always with astronomy, we have to take a look at additional galaxies, additional missions that are coming out, and look further into Alpine data. I look forward to where this work goes in the future, getting to work a little bit more with Dr. Kumari, and thank you all so much for listening. Do you have any questions?
Wonderful job. Do we have any questions for MJ? One over here.
What is dustiness?
So, it is genuinely just the dust content of a galaxy. Galaxies are made up of ionized and unionized gas as well as dust. Ionized gas is what forms stars. Dust is what forms kind of everything else in a galaxy. If you look up at the Milky Way, all of those dark patches that you see along the bright swath of the Milky Way are dust. In older galaxies like what we were studying in Alpine's data set, there is less organized and often more dust kind of squished around the shape of the galaxy. So we can say, all right, how dusty is this galaxy and how is that affecting what's actually going on with the dynamics of it? But it is genuinely tiny bits of basically sand.
Awesome, thank you. We only had time for one question, so we're going to go to the next one. So let's give her another round of applause, please.
I mean, you all can take my job. It's fine. No, yes, thank you. We have Sanaya, our AAS and Team Up Together intern. So give a round of applause for Sanaya.
All right, my name is Sanaya Leslie, and this summer I worked with Dr. Rice, AAS, and Team Up Together to gather student feedback and analyze what they said in order to make Team Up Together and AAS better suited for students. So the American Astronomical Society is the largest group of organized astronomers. It has over 8,000 members, and they are mostly known for their astrophysical journal. This journal publishes new discoveries and developments in physics and astronomy. AAS's overall mission is to make astronomy more diverse and inclusive, so they engage in things like science communication to make science more accessible to the public. Okay, sorry. Okay, Team Together is a program that was launched in 2022. This program was created in order to relieve some of the financial barriers that African-American students face and also barriers they face in their institutions. So they are mostly known for their scholarship program. This program awards $10,000 every single year to about 80 to 70 Black student physicists. They are also known for their Grant Excel program. This program awards $200,000 to 5 physics and astronomy departments in order to help Team Up Together implement their goals. So this summer, I went to Alaska, and these are some photos that I wanted to show you guys. The photo on the left is just me crossing over the Great Lake when I was going back home to Alaska. This photo at the very top is a picture of Alaska at 11 o'clock at night. And this picture is a picture of me. I had dinner with my mentor because I celebrated my 23rd birthday. And this is a picture I took when I took a little road trip to Gerwood. So the reason why I was in Alaska was to attend the AAS Summer 2025 conference. I attended the conference to interview undergraduate students so I could get feedback about the conference and their thoughts about their undergraduate experience. So some of the things I heard from the students at the conference, there were a lot of successes. A lot of the students told me that they felt very welcome in the conference and they felt very supported by the people there. A lot of them were telling me that they felt more affirmed in their physics and astronomy identity. Before coming to the conference, they felt a little out of place, and they said that with the interactions they had faced at the conference, they felt more secure in calling themselves physicists. Some of the challenges that I noticed at the conference was the lack of undergraduate programming. So a lot of students wanted information about grad school and career opportunities, and there were really no events dedicated to those topics. And all the students wanted to go to graduate school, so there was no resources for them to get information about graduate school specific programs. And a lot of them also wanted more networking opportunities between themselves and professionals. So they would have liked to see more networking or more networking events in order to get more feedback from professionals and what it's like working with grad school students and what it's like working in industry. So after I collected all the feedback from the AAS students who were at the conference, I wrote a report, and that report details all the recommendations that the students want to see at future conferences and what things went well and what things could be improved on. So moving forward, I will give that report to AAS for them to use that for the future and make their conferences better structured for students and make sure students go to their conferences getting all the questions they have answered. So next year, AAS will be holding their annual winter conference in Phoenix, Arizona. So last year, I attended the Team Up Together Student Experience Conference. Unlike AAS, this conference was entirely student-focused. So all the programming were focused on undergraduate students and Black physicists. So this program was dedicated to all of the students who had won the scholarship for 2022, 2023, and 2024. So I was able to experience this conference, and I had a really good time. Now, the reason why I included that slide was because I did work with Team Up Together and Team Up Together with WestEd. And WestEd is a company that evaluates educational programs. So right now, Team Up Together is undergoing an evaluation, and this evaluation will just assess what Team Up Together is doing well and what Team Up Together needs to work on. So in order to implement that process, Team Up Together sent out a survey to the scholarship recipients, and my goal was to analyze the quality of data from the surveys. So in order to do that process, we do this process called coding, and coding takes the qualitative responses and organizes them according to themes. So based on different questions and different responses, some of those questions and some of those responses have overlap. So in order to make all the information more digestible, we organize them and group them into themes, and then using those themes, we develop codes, and those codes go into a report that has everything neatly packed together so they can input that report in the report they'll give to Team Up Together. So some of the things I noticed in the surveys concerning the program and the conference, the successes, especially at the conference, was the same I heard at AAS. A lot of the students felt more firm in their physics and astronomy identity, and AAS and Team Up Together both created a welcoming environment at their conference, and a lot of the students expressed high satisfaction with the scholarship and the conference itself. Some of the challenges I noticed in the survey were that students wanted more post-undergraduate support. So a lot of students who don't want to go to grad school and who want to go into industry don't really know how to navigate that avenue. So they would like to see more support from Team Up Together in order to help those students who are kind of in between positions of not wanting to go to grad school, but wanting to go to industry and not knowing how to get into that field. And also at the conference, they wanted more networking events. There were a few networking events dedicated to students so they could meet with professionals, but students wanted more longer networking events, and some students wanted a virtual event in case they couldn't go because of travel conflicts. So for the next steps at Team Up Together, they will be hosting their 2025 student conference. West Ed and myself will be there conducting focus groups with the 2025 scholarship recipients. So for this conference, this focus group information is going to be written down and transcribed, and this information from the focus group will be put into a formal report, and that report will go to Team Up Together to for them to analyze what's going well and what's not going well. So with the impact of my work, the feedback that I received at AAS and what's compiled in the report will be used by AAS in the future so they can make conferences better suited for students. And West Ed's evaluation and Team Up Together will also help them from the report figure out what the program is doing well and what they need to work on in the future to make sure all the students get what they need. And I would like to thank my mentor, Ms. Knowles, Jacqueline, Selena, and Sylvia Martinez.
Fun.
Thank you, Sanaya. That was wonderful. Do we have questions for our intern?
What surprised you the most about working with both AAS and Team Up Together this summer?
I think looking at the surveys, I feel like Team Up Together did a really good job of making sure that students felt welcomed at the conference, and the fact that everyone that did the survey expressed high satisfaction. So there weren't really any negative comments about the program and the conference itself. So I was really surprised to see that most of the students and all of them had very good experiences with the program, because that's not always the case. But everyone benefited from the program. With AAS, I was mostly surprised at the conference to meet students who were very well prepared and who were very excellent in the research they were doing and things like that. All the students I talked to, again, had all positive things to say about their institution and their mentors. So I thought that was surprising because that's not always the case. But it's just nice to see that physics and astronomy is very positive overall, and people are benefiting from being in this field.
Awesome. Thank you so much. Give another round of applause, please. Before Maya beats me to it, I want to introduce our Physics Today intern, Maya. And this is also her second year, so double round of applause.
Oh gosh, I'm dropping this mic. Well, it landed on the ground, so. Hello, everybody. My name is Maya, and I was this year's science writing intern at Physics Today. I'm going to be talking a little bit about the magazine itself, what it was like to write for them this summer, and what I learned and accomplished. So, I hope all of you know Physics Today. I hope you all read it. Physics Today is a news magazine that's published by AIP. It comes out in print every month, though we are moving online first, and it covers the richness of physics research and the experience of the people who do that physics. So one may ask, why is a field-specific magazine like this one even necessary? Can't people just read journals? Well, research is very complex. Reading something in your subfield already requires a lot of attention, and sometimes things outside your subfield can feel pretty much incomprehensible. We want to make that research, that groundbreaking physics research, easy to understand for people with different scientific backgrounds to unite the physical sciences. What that includes is A, making that research compact and concise, B, reducing that technical language, and C, writing an accurate story. The head editor of Physics Today, Rich, likes to say, where our job is not to write, it is to be read. He really likes to say that. So I'm going to give a very basic 5 steps to an article. Mega disclaimer, this is very simplified. It doesn't work this smoothly. So step number 1, identify your story. When you're pitching a story, as I've learned, you have to think about what is interesting, where you see the story, and most importantly, whether or not it is of interest to your readers. 2 of the stories I wrote this summer were things that I pitched. As you can see on that far right over there, you have this purple image with a green laser shooting through the sky. That was a backscatter on the Martha LiDAR in Germany. I felt like this image was visually interesting. And I could write about being able to use fluorescence to detect new layers of pollution in the atmosphere, and I thought that was cool. I also pitched a story on the intersection of poetry and physics, because I wanted to read more about physics and art. And then 2 of the stories I wrote were assigned to me. This is a really, really cool photo of the first observed double detonation of a supernova, and I got to write about that. And then I also got to write about the International Physics Olympiad, which is a story interns usually write. What is exciting about this year's International Physics Olympiad is that the US team came home with 5 gold medals, and they were the only team to come home with 5 gold medals in, honestly, a hot minute. So step number 2 is research. You have to reach the science at a level where you understand it. You don't have to understand all the details, but you need to be able to talk about it and simplify it to yourself to write it without jargon. For me, this was a lot of reading papers in depth and annotating them, and also explaining it to myself and to other interns. It involved identifying experts and asking questions. I conducted some interviews with poets that are also physicists, the International Physics Olympiad competitors and organizers for the US team, and yes, those are the interviews I conducted. I sent many, many emails to researchers and also poets, and I used my peers. Thank you to MJ for answering so many questions about this supernova paper. Step 3 is to write. This is one of the final drafts of my International Physics Olympiad piece. For me, this process started with noting the key ideas that I wanted to hit and to keep in mind some words that I thought were cool and I wanted to use, thinking about the focus, the logical flow, being able to use accurate language, thinking about how those paragraphs transitioned into each other, and sticking to the PT style in language and amount of detail, which was difficult. And then step 4, the longest process, was revision. These are just some of my drafts. And this process included so many rounds of edits with both the editors, thank you, Andrew, and fact-checking with authors of a paper. I learned to take constructive criticism better, and also to trust my own voice and keep in what I felt like was important to the article. I also got the chance to edit somebody else's submission to PT, which was just a really interesting experience. I did an internal review of a quick study about artificial muscles. So quick studies are articles that explain some kind of physics concept at an undergraduate level, usually based on some everyday phenomena. Some of the last few have been about ballooning, static electricity, and the luminosity of things in the universe. Doing this internal review was a very different analytical perspective. I had to think about how to provide clear feedback and take a more zoomed out lens, thinking about how to restructure things as a whole. And I think it made me trust my own judgment in that a little bit more. So what are some of the things I learned? First off, reading a lot and broadly is really important to being a good writer. And a story can be defined really, really simply. So you can be like, it's a series of ideas that get you from point A to point B. And if you're using that definition, what of those little steps can you take out to make your story more concise, and does that story still hold when you do that? I also don't remember ever having an explicit grammar lesson in my education, but I did this summer thanks to the PT copy editing team. I learned about restrictive and non-restrictive text. In the editing and writing process, I began to pay a little more attention to using different kinds of paragraph and topic transitions, thinking about sentence length to balance momentum, and being really, really deliberate with my language, thinking about rhythm and the accessibility and familiarity of that language, and also trying to be vivid with as few words as possible. I also learned that there's so much more behind the scenes of creating a news magazine than I thought. There's so many more rounds of editing than I thought there were. There's so many back and forth with so many people involved. The copy editors, the proofreaders, the arts team, the researchers, and then also editing all those solicited articles and defining what is in a singular issue. So step number 5, the most exciting, glory-filled stage, publishing. So these are 2 of the articles that I published this summer. One was the atmospheric aerosols with the Martha LiDAR, and this one is the supernova explosion one. I have 2 more articles to come. One about poetry and physics, and one about the International Physics Olympiad, both of which I have completed, kind of. Andrew's giving me a thumbs up, so I can say completed. So thank you so much to my mentors and also everyone at PT who read my work and gave me so much feedback and answered all my questions, and also the SPS team. If you would like to read the articles that have been published, there are these QR codes, and you can email me at that email.
Awesome. We have time for a question.
Thanks. So Maya, what were you most proud of either learning or producing during your time at PT?
I'm pretty proud of the physics and poetry article. It was an idea that I had and then I pitched, and it was accepted even though it's not really in the usual well of what PT does. And it was a very long process. It's a Q&A plus an intro and a few selected poems. And it was originally just going to be just a Q&A, and then it got turned into a feature, which is really awesome. And there was just a lot that went into that, and I'm proud of that whole process. It was pretty lengthy. Yeah.
We have time for one more quick question.
Thanks, Maya. How do you decide how long your articles should be? And I guess it depends a bit on your topic, but how do you, as like a writer, decide?
Well, for the things that I wrote this summer, some of them had very clear word limits, so the backscatters are usually about 200 to 250 words. The feature article was originally a Q&A, and the Q&A is supposed to be between 1,200 and 1,500 words. And so there were like limits on that. And then I guess it depends on when the story is done telling. And how much detail you feel like is necessary to make that comprehensive and concise. Yeah.
Was there one more question? No. Okay. Oh.
Awesome presentation. Are you going to
Thank
keep
you.
writing?
Are you going to keep writing?
Oh, am I going to keep writing? I hope so.
Awesome. Thank you. Another round of applause. Awesome. All right. So we have our next presenter is JJ, who also went to Michigan State University, which is also my alma mater. Go Green.
Go White.
And he's also our Mather policy intern. So round of applause for JJ.
Hi, everyone. So, as Kayla said, I'm JJ DiFio. I am a Michigan State University student studying politics, physics, and philosophy, and I was one of the 2 John Mather Science Policy Interns at the NIST Office of Advanced Manufacturing. My project was on quantum initiatives at NIST and their applicability to advanced manufacturing. So just as a quick overview of NIST, NIST is a part of the Department of Commerce, and it is a national laboratory. So it does a lot of science-related things with the goal of promoting commerce and promoting the economy. So a lot of that stuff is the services and resources, providing standard reference materials, standard reference data, and then it does a lot of true science in the laboratories in this middle section. And then where I worked was in the extramural programs, which are the outward-facing programs. And right there is the Office of Advanced Manufacturing, where I worked this summer. So what is the Office of Advanced Manufacturing? It is a national program office at NIST that oversees and coordinates advanced manufacturing, and it supports the National Science and Technology Council Subcommittee on Advanced Manufacturing. And how it does this is it supports the Manufacturing USA program, and that is a network of institutes, 18, soon to be 19 institutes, all focusing on a different field of advanced manufacturing, as well as a bunch of interagency partners that all contribute to the program. It also contributes to funding manufacturing-related programming. So I said quantum initiative, but to define what quantum initiative is for the purposes of this presentation, I defined it very broadly to be research into or using quantum mechanics, and then the initiative half of it is research into technologies that leverage quantum phenomena that in some way accelerate, advance, or contribute to domestic manufacturing. And so my research focus was creating a catalog of ongoing NIST quantum initiatives, assess each project's applicability to advanced manufacturing, and then find how these projects, these initiatives at NIST overlap with other programs going on. So the key products that I produced were one big main report. It was 26 pages long, sorted by application area, as well as by NIST internal organizational structure. And this was so that you could either go and look for relevant application areas to what you're looking for, or be able to look how you can make connections and see who you want to reach out to do this. Then my other parts, the sub-reports that I wrote 2 sub-reports to institutes, one to the National Institute for Innovation in Biopharmaceutical manufacturing biopharmaceuticals, and Smart USA, which is the Semiconductor Manufacturing and Advanced Research with Twins Institute. Those are about 4 pages each, and they highlight work and expand on work in the main report, explaining what work is being done at NIST that's relevant to those 2 institutes. And then my third sub-report over here was on the NSF innovation engines and the Economic Development Agency tech hubs, innovation tech hubs. And what I did here was map. We have a previous work in our office by a AAAS fellow that created a huge spreadsheet of all ongoing NSF engines and tech hubs. And so I pulled out the quantum-related ones, and I found what work they are doing and how that overlaps with the work going on at NIST. So why does this matter? Like I said before, OAM is a coordinating office. We are that center gear there, and without us, we enable so much other work to go on. And we enable all this work from all these different interagency partners. And to be able to do that work of coordinating all of this ongoing programming, we need the information about what's going on so that we can monitor this work, monitor for updates, developments, and be able to disseminate this to our partners so that they can be aware of work relevant to them and how it can help them. We didn't have a list of this available, and especially we didn't have anything that assessed for manufacturing applicability, which is very important to our work. So part of my findings is that I found that at NIST there are roughly 5 main categories of quantum initiatives. They fall into material science, quantum sensing, biopharmaceutical and biomedical, photonics communications and quantum networking, and semiconductors/quantum computing. Here are some examples of them. The coolest ones, probably quantum sensing and photonics and communications. I'm running low on time, so I'm going to skip explaining them, but there's some really cool stuff going on that you should look into. Timelines for this stuff. Right now, there are products being produced with biomedical and pharmaceutical, as well as material science applications. These are a lot of imaging tools and that sort of stuff contributing to the field. Soon, quantum sensing. Quantum sensing, like I said, very cool stuff. We have quantum sensors now in some forms, like MRIs, but some really advanced stuff like advanced calorimeters and accelerometers are coming very soon. Next 5 to 10 years, they'll be commercially available. Later, photonics and communications/quantum computing, a lot of the quantum networking stuff, we don't really know when there's going to be utility scale quantum computing. Some reports said 2026, some reports said 2046, so I have Schrodinger's cat here because it is both next year and a few decades from now, so we're not really sure. So how will my work be used? It's we need to be able to plan for this ongoing increased focus in quantum research. Everyone is always talking about quantum, how can we leverage quantum, how can we manufacture quantum, and so we need to be able to plan on advising leadership on what aligns with our goals, what work is being done, and how can we contribute to it, how can they contribute to our goals. We want to promote cross-divisional and interagency collaboration among scientists, because there's a lot of work going on that can be benefited by collaboration, as well as promoting collaboration between scientists and policymakers and government, because government and policymakers can't properly policy make if they don't know what's going on. Reflections, I was a very small cog in a very big machine of the federal government, but I was really proud to have contributed in the way that I did. It was amazing to learn NIST's customs and personality of the agency. It was really cool. This work really needs physicists. I can imagine my political science friends trying to explain how a quantum doohickey, addresses biopharmaceutical advanced manufacturing, and it would not go well. So I'm very appreciative, and I want to continue pursuing public policy. I would find myself wondering, how can Congress better legislate this? How can the executive branch better policy make for this? And I'm excited to continue contributing to missions like this in public policy. I want to acknowledge everyone on this list, but especially my mentor Susan and the coordinators Brad and Lisa over at OAM, who did so much paperwork and helped me out when I was stuck at the badging office every week. And everyone else on the list as well. They were amazing and supported me so much. Thank you. Any questions? This is my contact info if you want to get to me.
Awesome. We have time for one question.
What's the next step for the Tech Hub NSF Engine sub-report? Where's that going?
Yeah, so that report is, first we're going to look at, our office is going to look at it and see what overlap there is, and see if there are connections to be made, see if there's connections between NIST and there, see if those connections align with our goals, and determine, that's really is the question, is what is our next step? Because that's, a lot of it is the planning process is what these are going to go to. So a lot of analysis really is the short answer, is we're going to use this for a lot of thinking.
Awesome. Give it up for JJ. Awesome. Now, next we have Grace, another AIP Mather policy intern. Give it up for Grace.
Thank you. Thank you, Kayla. So like she said, my name is Grace, another AIP Mather policy intern working at NIST in the Office of Advanced Manufacturing under Department of Commerce. And so I'm going to be talking about my project on the mapping of the data ecosystem across the federal government. Before I get super into it, I'm going to give you another super quick breakdown of where we were working. So again, we're at the National Institute of Standards and Technology, which serves as the National Measurement Institute of the U.S. So it means, among a lot of other things, it's defining units like the kilogram, the meter, and the second, which is really cool. Also setting standards and driving innovative research that's used mostly in industry is kind of the big goal of NIST. It can be thought of as industry's national lab. So a bit of a different focus than some other national labs. And so within NIST, we're in the Office of Advanced Manufacturing, which is externally facing. And it's the home of Manufacturing USA, which is a public-private partnership, a network of different institutes, all focusing on different technologies. And so as a public-private partnership, each institute is comprised of members that are in the federal government, in industry, and in academia that are all working together to drive technology transfer from research into large-scale manufacturing. And when you think about a lot of research happening today, AI and big data are kind of a lot of buzzwords that get thrown around, it seems like, that just about every new paper has AI on it. And so it's really good to look into what initiatives are happening across the government to be able to drive that. And before I get into it, again, since big data can be such a buzzword today, I want to talk a little bit about what it actually is. And so we know traditional data and how we manage it. We've all used Excel, I'm sure, but big data is not able to really be handled by those typical systems for a variety of reasons, and it's typically characterized by what we call the 3 V's, which are on this figure. One being velocity, so our data is constantly being produced, we're constantly getting more data. Volume, there's a lot of it. hence big. So IBM estimated that there's over 400 million terabytes of data generated every single day. I'm sure that number's gone up because that was estimated a few years ago. There's also a lot of variety, so different data types, but also a lot of differences in the way it's stored and the way it's structured. And most of this data isn't structured at all, which can be problematic. So in addition to just purely computational issues, there are a lot of other challenges to using big data for more practical purposes. And I'm not going to go over all of them for the sake of time, but just to quickly touch on one that's really big in the manufacturing industry is data interoperability. And so like I said, there's a lot of variety in the way our data is structured. And so this can become a problem if one system is producing data, it's naming it, it's structuring it in a certain way, it passes it along to a different system, and then it's not able to use it because it doesn't understand it. And so data interoperability is the goal of all of these different systems being able to use the same data because they're structured similarly. And this comes into play in manufacturing with biopharmaceuticals in continuous manufacturing. And this is something that's being worked on by Manufacturing USA Institute to be able to have continuous manufacturing be a new thing, in addition to the development of lots of new sensors and things that are above my pay grade. Data interoperability is a big goal to be able to make this achievable. And continuous manufacturing, so traditionally, we have a big batch of some sort of biopharmaceutical sample, and in between each stage of manufacturing, it has to be taken somewhere else to be tested for certain critical quality attributes, such as pH, temperature, maybe different sugars that have bound to it, to make sure it's kind of on the right track in the manufacturing process. And then manually, certain parameters may need to be changed to ensure that at the end of the day, the final product meets certain standards. So with continuous manufacturing, the idea is, again, to have sensors producing that data in real time, but also other systems that are able to interpret that data and decide on new parameters to be used all at once, which increases the efficiency of the entire system. Again, big goal. But what things are being done throughout the federal government, kind of switching away from manufacturing for a second, just wanted to look at what is a priority for different federal agencies within big data. And obviously, all of these agencies have very different goals, very different budgets and things that they're able to do, but how much kind of are they prioritizing being able to use big data? So just to highlight two of these, the Department of Defense, they've had an agency-wide data strategy for several years now with a multi-billion-dollar price tag on that. But looking at something like the Department of Energy down in green, prior to this year, they focused mostly on providing grant money to specific projects that are working on addressing certain challenges in big data, maybe looking into AI or machine learning. So I looked into a lot of the differences in what these different agencies are doing. But again, this is a very big ecosystem. So just zooming in a little bit on what NIST is doing within all of this big data hubbub. And so NIST's biggest role is in standards. It's in our name. It's great. And so I talked about data interoperability, and one really great way to solve that is through the development and implementation of standards like ontologies, which is how our data is named. And so NIST is accelerating the development of standards, helping implement them into industry in a variety of different sectors. But one big place where that's happening is within Manufacturing USA in those institutes. One example being at NIMBLE, which is the Biopharmaceutical Manufacturing Institute. And so that's housed in the Department of Commerce, which means that NIST is hard at work in their big data program. Specifically, one of those projects is working on developing an ontology that can be used across all industry partners. All right, so just to quickly wrap up, big data has a lot of really big uses. It can be very powerful, but it requires a lot of additional effort. And it also requires a lot of collaboration because of how large the challenges facing it are, which means that the intervention of government can do a lot of good for being able to use big data. And these public-private partnerships, such as Manufacturing USA Institutes, can help bridge those gaps. So I've been able to do really in-depth critical analysis of what is currently being done, and so where there are needs within this industry. And my work is likely to go towards a public-facing technical report to help get this information out to the public. And then very quickly, do want to highlight, in addition to this big project, I was able to work across all the divisions at OAM, doing things such as social media management or like highlighting certain stories, and also just do a lot of tours around NIST, learn a lot about manufacturing. You'll see down there we brought the other interns out to NIST, and they got to take a little picture with Newton's apple tree, which was super fun. So just very positive experience, and I've learned a lot about what physicists and scientists in general can contribute to policy and what those careers look like. And just want to thank everyone here at SPS and AIP, everyone at OAM who have taken over this little corner, that have all been extremely helpful, very supporting me, and also all of my professors back at Rhodes, that I wouldn't be here without them. So thank you all so much for listening, and I'm happy to take any questions you may have.
Thank you, Grace. We have time for one quick question. Oh, I didn't have to go anywhere.
So generalized, what did you see in the differences of strategy between the funding levels of these agencies and their approach to data universalization, I guess?
Yeah, a lot of it was just kind of in the scale of it. So that's why I kind of picked, I can go back to the table too if that will be helpful to have more time. But looking at the ones with the kind of higher price tags like the DoD or HHS, they had very broad-reaching initiatives that kind of wanted to cover everything that they do. So again, the DoD, that's a very, very large organization with a lot of funding, but looking at like the HHS, a lot of that had to do with like the NIH and the CDC, that they have very large programs for data sharing in healthcare and also in like disease mapping and stuff like that. And so I think the biggest difference is like the size of the kind of like industry that they're covering, and that they're wanting to bring all of it in together versus, again, looking at like the DOE or even like NASA. Like a lot of what NASA has is more like, okay, within this certain area of astrophysics, we want to be able to share all of this data versus over all of healthcare in the US. So if that answers your question.
Awesome, thank you. Give it up for Grace. Next, we have our AIP Niels Bohr Library and Archives Center for History of Physics intern, Kaylin. Give it up.
All right. My name is Kaylin Stefanik. I'm the Niels Bohr Library and Archives and Center for History of Physics intern. And today I will be presenting on transhistorical narratives and looking beyond identity. So first, let's start with a quick show of hands. How many of you could name a transgender physicist? Or even just a transgender scientist? Okay. More in this room than usual. But this exercise highlights the reason that this research is so important, because there is such a huge gap in representation in physics and the history of science in general, not just for trans people, but also for other minority groups as well. I could ask you the same question about disabled physicists, for example, and maybe with the exception of Stephen Hawking, many people would not be able to name any. So over the course of the summer, I worked on a bunch of projects. Most were centered around the transgender and non-binary community. However, I was also able to do some archival research on disabled physicists as well. So I visited the American Association for the Advancement of Science archives to view their collection on the Project on Science, Technology, and Disability, which started in 1975. And in one of the many aspects of this project, Robert Menchel, who's a deaf physicist, took a year of sabbatical from his job to tour schools with disabled students across the US, and he advocated for accessibility not only in scientific careers, but also in classrooms and curriculum for schools for the blind and deaf. And although conversations about accessibility were clearly happening in the broader science community long before federal legislation like the ADA was passed, a search through the American Physical Society archives showed a little bit of a different story. So the first mention of accessibility efforts at APS was in the Task Force on Physicists with Disabilities, which was founded in June of 2000, which was 25 years after the AAAS project. So as far as accessibility is concerned, physics continues to lag behind the rest of the sciences, unfortunately. To learn more about this, you can read the post that I authored for the NBLA blog titled Ex Libris Universum, which should be published in the coming weeks here. I also kickstarted a Wikipedia edit-a-thon on trans and non-binary physicists. So Wikipedia edits are especially important for physics history outreach because they are so widely available. Anyone with an internet connection can access them. So articles that are less developed are often less likely to be featured on the Wikipedia homepage, and articles without images or info boxes also do poorly in Google search results. So I originally identified about 30 articles to focus on, and the goal was not necessarily to do in-depth editing of these articles, but to make strategic edits that would have the most substantial impact, such as updating info boxes. So we removed dead names on articles and lists and adjusted pronouns and honorifics to match their current gender identity, just like the one for Jan Eldridge, which you can see here. We also solicited and added images for articles, including Megan Povey, who's a food physicist, and you can see her. As a result of the edit-a-thons, about 2,000 words were added to 25 Wikipedia articles and lists, and that totaled over 22,000 views total on the published edits just so far. So as you can see, that's a pretty huge impact just already. I do plan on continuing my work after this internship just because there is so much more to be done. Out of the Wikipedia edit-a-thon, a new need arose, which was the need for guidelines on how to write about transgender physicists. So Wikipedia's style guide on writing about trans people was a little bit out of date, so I could not rely on that for the edit-a-thon. There were a few various guides online that were just about transgender people, such as GLAAD's Transgender Media Reference Guide. However, I wanted to focus on the specific needs to cater to physicists and other scientific professionals. So after consulting multiple formal and informal guides that were online about transgender people, I compiled a list of best practices that applied to the specific concerns of trans physicists, such as dead names on former publications. And you can see I've highlighted a few of the practices on the slide here. My main project this summer was conducting historical research on Alan Hart, who was a radiologist, tuberculosis researcher, and medical physics pioneer. So he was born in 1890 and lived until 1962, and he had a pretty remarkable career. He pioneered the use of X-ray diagnostic imaging for tuberculosis, and also helped operate numerous mass X-ray clinics across the country to screen thousands of people for infection. So you have to remember this, much of his life, it was before antibiotics were created to treat TB. Those were created in the 1940s. And the only hope for patient survival at that point was early detection, and Hart knew this. So he employed X-rays, which were critical for early detection because a lot of times symptoms were not displayed until later on. So he also wrote a book describing X-ray technology for the general public, which was called These Mysterious Rays. And this book was translated into Spanish as well as a bunch of other languages. And it was, and in many ways still is, a gold standard explainer on X-rays for the general public, which is pretty cool. He also traveled to a bunch of different towns and hospitals across the US, giving hundreds of public lectures on various topics concerning radiology, research, and also some general public health things as well. Now, while working as a consultant for the Idaho Anti-Tuberculosis Association, Hart authored a weekly public health column in the local newspaper, which was called the Lewiston Tribune, and he did so for around 2 years. Now, the really exciting part about this, I actually happened upon this newspaper column accidentally, but I had not seen any other historical sources mention this, so that gives me reason to believe that I was one of the first researchers to discover this aspect of his career, which is really exciting. Hart worked as a public health advocate for the Connecticut State Tuberculosis Commission in the last part of his life, overseeing a huge statewide X-ray screening program that helped save a ton of lives. And now with accomplishments like this, there is no question that he is obviously a very significant figure in the history of medical physics. However, the majority of publications about him are actually in a different field, women and gender studies. So Hart is more well known among gender studies scholars for his gender transition. So in 1917, he was the first trans man in the United States to undergo a hysterectomy for purely gender affirming reasons. I would argue that while his trans identity is really important, it should not be the sole thing that he is remembered for. He contributed so much to medical science that deserves to be highlighted. And this is one of the things we must be careful about when we are doing this filling in the gap of historical narratives, that we should not center them too strongly around just their minority identities, but we need to highlight every aspect of their career. Now, as we move into the present day, oral history narratives are an incredible tool to preserve the authentic experiences of minorities in real time. I had the pleasure of doing oral history interviews with Jessica Mink. She was part of the team who discovered the rings of Uranus, among many other accomplishments. And one of the insights that I want to leave with you all today is that I want to impart that people have many different identities. A fundamental part of her life is her identity as a scientist, and I think as physicists, we can all relate to that. Her accomplishments, as well as those of many other transgender scientists, should transcend diversity, equity, and inclusion initiatives, and we should be discussing trans physicists not just because they're trans, but also because they have contributed incredible scientific contributions to the community. And thank you. Any questions?
Thank you so much, Caitlin. Congratulations on your discovery as well.
Thank
Do
you.
we have time for one quick question? I'm gonna sprint across here. I'll run for you, Arlene.
Thanks. What was the most surprising thing you learned in your research?
Yeah, I think the most surprising thing, honestly, I think was that, well, there were a lot of surprising things, honestly. That's a difficult question. I think to highlight one of them is just how little people actually talk about the contributions of minorities in science. There's a lot of things, like if you Google Jessica Mink, for example, or Jan Eldridge, even Alan Hart, like things come up about their trans identity. That's easy to find. You can find their advocacy. However, finding their actual scientific research is difficult a lot of times, and a lot of people have not written about it, or if they have, it's not the focus. And so I think that's kind of the main thing that I wanted to talk about today, is that it's really surprising, and I think we need to do better as a physics community to fix that. So yeah.
Awesome, thank you. Let's welcome our next presenter from the Department of Defense, Sunny.
Hi guys, so like Kayla said, my name is Sunny Rasmussen. This summer I worked with the Department of Defense in the Office of the Secretary of Defense in the Cost and Assessment Program Evaluation, or since in the government we really like acronyms, DoD, OSD, CAPE. So I'm a senior at the University of Utah. I study physics, astronomy, and political science, so this was a perfect internship for me. So in my internship, I worked on planning P-Leo constellations, and we'll get to what P-Leo means. So in this presentation outline, I will go through the problem, the methodology, the analysis, conclusions, and future research. So what is P-Leo? Well, P-Leo, the P stands for proliferated. Leo means low Earth orbit. So when we're talking about satellites, we're talking about P-Leo satellites, which means satellites that are orbiting low to Earth comparatively to like astronomy ones, like MJ's presentation with different sort of satellites that are orbiting the Earth and getting telescope data. Those ones are orbiting at a really high altitude comparatively to low Earth orbits, which are a lot smaller orbit-wise, altitude-wise. And so why are we talking about P-Leo, and why is the DoD interested in P-Leo? Well, a lot of DoD people, as well as other satellite architecture owners, are shifting to P-Leo because they're less expensive and they create a tactical advantage because there's going to be a lot more satellites that are a lot harder that are a lot easier to defend if there's a lot more of them. So because the DoD is building budgets and then because my office is looking for budgets many years out in the future, we want to make sure that we're buying satellites at a correct rate and that we know what the most optimized way to send them up is so we can save the money. So we need to think about satellites as a system and build them as a system. All my research is taken from open source data that you can find on the internet. So because of this, I took internet data about SpaceX's Starlink. So we chose Starlink because they have thousands and thousands of these P-LEO satellites that they've already been launching for a couple years now, which gives us data on when they decay as well as how long they're able to be useful for. So from this, in the methodology, we'll be deriving a decay rate as well as using queuing theory. Now, what's queuing theory? Queuing theory is basically the math of standing in a line, which is pretty boring sometimes. But when you really think about how you can apply the math of standing in a line, you can also apply it to the math of a satellite decaying or falling out of orbit and waiting, instead of waiting in line, waiting to decay. So you can see here in this graph that Starlink has a lot of satellites. So starting out in 2019, they only had a couple. But by the time you get to 2025, at the time that this graph was made, they had near 8,000. By the time that this presentation was finished, they had about 9,000. So they have a robust data set, and they've already had a couple, many, and you'll see in the next slide, that have decayed, which gives us a good model of their expected lifetimes. So from this, we can create that model to use and create different levers to pull in order to optimize satellite lifetimes and the money we can save there. So you can see in this graph that this is the time to decay in years, and these are the number and rate decay of satellites. You see, note here that these Starlink satellites are starting to decay about year 4, and that their lifetimes, and at the time that this graph was created, it was only about 5.5, but by the time that this project was finished, their lifetimes are about 6-ish years or so. So they're not living very long, but they're really useful and they are a lot cheaper to send into a low Earth orbit. And so this decay rate gives us data on when they actually are decaying. So using this, we can create a couple different models using hazard rates. Hazard rates are related to the queuing theory, the waiting in line, the waiting to decay. So because of this, we're able to do a lot of fitting to our data, which is just different methods when you use statistical data. So we want to focus in on this graph right here. This graph's shape tells us that we're able to fit it to a thing called a Weibull function. The Weibull function is a little bit funky to understand, and I'm not sure if I fully understand it in the short time that I've been working here. But I do know that the Weibull function, when we get a shape like this, and it's a little bit convex, which means it's going to be outward, and that it gives us a value of k is greater than 1. In this case, we have a k is equal to 1.8. That means that we know that the thing that is dying or decaying is dying because of mechanical failure rather than random failure or just a high infancy mortality rate. So that's really, really good news in our case to know that Starlink satellites and satellites in P-LEO are dying from mechanical failure rather than just random chance. That allows us to actually build a model. So we can see here that now that we know the idea of what kind of model we want, we can start actually thinking about what does it mean to actually be building a model for different satellites. If you think about something that's orbiting, there's a lot of different places it could be orbiting. There is almost infinite combinations of where something could be in space. And so we decided to think about satellites in terms of planes and in terms of satellites in those planes. So you can see in this picture, and this is not a P-LEO orbit at all. This is actually a highly elliptical orbit. This is the kind of orbit that astronomy satellites, astronomy telescopes are in. But just for a reference, you can imagine one of these circles as a plane, and that these 11 dots are different satellites on those planes. So it's basically just two numbers we're multiplying together to equal a constellation. So in this case, we can think about these satellites in terms of planes and number of satellites in those planes. And we can build something called a Monte Carlo simulation in order to get different iterations to be able to figure out what is the most optimized number of planes and satellites for longest living constellations. So in this case, I use 3 planes and 20 satellites just for one iteration of a Monte Carlo to see that this combination of this constellation of 3 planes and 20 satellites is going to live for about 2,500 days. So you can see here, this is the number of satellites on this axis. We're starting at 20. Each of these lines represents a plane, and this number, this right here, shows us when a certain plane hits a threshold where that is rendered a useless orbit or a useless plane at that point. So you can see here that the first one, the blue line, is rendered useless about right here in terms of days, and then the rest of the constellation is rendered useless about 2,500. We decided to use this value, this what we call a tau value, to be half of whatever the number of satellites was, which is 10 in this case because there was 20 originally. So now we have a model with different levers we can pull, different plane combinations, different mixing and matching of different numbers of satellites, which is really great because now we can figure out how many years different mixes and matches of combinations live. So overall, we did not find a single idea of what to do yet, since there's so many different mix and matches values to find. But we do know that this is a thing that the DoD can use in order to make sure that we optimize when to buy satellites and when to send them up. So we did find, though, in initial iterations, that there is a significant difference in constellation lives depending on the structures, which is what we were expecting. We also did find that the way to optimize these P-LEO satellites is to have more planes rather than more satellites. So if you're doing different numbers of satellites, you want to have 30 planes and 20 satellites rather than 10 planes, 30 satellites, if that makes sense. So this model can inform how the DoD is saving money by planning these P-LEO satellites in an optimized way. So in the next steps, we're going to be wanting to make sure that we actually nail down a correct number of planes, correct number of satellites that also fits the DoD's budget and what we can afford through Space Force and other organizations to be able to figure out how many to send up and when. We will also be able to vary these assumptions based on the altitude as well as the inclination of where these launches actually are going around. So I was really grateful for my time with the DoD, and this is really interesting work that I was glad that I could do. So thank you.
Thank you, Sunny. We have time for 1 or 2 quick questions.
Kaylin? Yeah.
Loved it. Good job. I had a question of your model. So it sounds like it's based on the satellites being sort of the same type of satellite. Are there sort of other variables that affect that mechanical failure for decay?
That's a great question and a very scientific-minded question. So in this case, for the simplicity of the model, we just assumed that each satellite was its own little black box, and it was just copy and paste, copy and paste. I'm sure on those satellites themselves, you might be able to get more into the specifics of how to optimize lifetime according to the machinery of them. I know coming from NIST and thinking about the machinery, that's definitely a way to be optimized. So maybe DoD will be reaching out soon to ask about how to optimize those. But that's just me talking.
We have one more question over here.
Hi, yeah, thank you so much, Sunny. I'm just wondering, I guess, given that satellite, constellations like you said, Starlink, are privately operated, and I guess subject to proprietary designs and operational choices, how can public sector models, especially those used by the DoD, I guess effectively plan around systems whose failure rates and design iterations and sort of deployment strategies cannot be fully disclosed?
That's a great question. So like I had mentioned throughout this talk, actually all of my data was from open source. So none of this is any secrets. None of this is behind closed doors. So you're actually totally welcome to recreate all of this through the publicly available launch and decay rates that Starlink has. So this isn't any sort of closed box, closed doors that the DoD has. So this is available to the civilians.
Awesome. Give it up for Sunny. Naomi, our AAPT and SPS SOC intern. Please give it up for Naomi.
Well, good morning, everyone. My name is Naomi, as Kayla introduced, and I this summer had the privilege of being the SOC and AAPT intern. SOC stands for Science Outreach Catalyst Kit. And I just want to tell you a little bit about the SOC. Who is the SOC for? The SOC is designed for SPS chapters, college students all around the country. And what it is, it's a box of physics demonstrations. I made 100 boxes this summer, and with them I include little write-ups designed for K through 12 students to describe what physics is going on. I've got tailored explanations for the physics, and so everyone gets a chance to connect with these physics demonstrations. Along with those demonstrations, I've made YouTube videos for each one of them to kind of give them an online guide for that. And why? Because physics outreach is very important. So this year I got to choose the SOC theme, which is SPY, and this kind of explores some topics in circuits, simple circuits, electromagnetism, heat transfer, light absorption and reflection, magnetism and magnetic fields, and then light dynamics. So this here is the telegraph that I designed, and this is one that I'm probably the most proud of. It's a very simple circuit that opens and closes at the transmitter, and then we have a little electromagnet right there that drags this tiny piece of nickel down and clamps it down. Whenever that circuit is completed, that electromagnet turns on, clicks down. And so we can send messages through Morse code. I completed 4 other demos. Up here in the right top left, we have invisible ink, so this is dealing with heat transfer. And I had a color decoder. We're thinking about light and how do we see light using different lenses. I created a compass. This was exploring topics in magnetism and why does our compass point to the North Pole when our Earth has its magnetic South Pole at the geographic North Pole. We had also a laser maze. This one is pretty cool, and it's all about reflection. And so the second half of my internship was with the American Association of Physics Teachers. And I got to kind of dive into topics in K through 12 physics, which is a very underrepresented field in physics. And I'm a preschool teacher where I'm from, so I have a special heart for K through 12 physics. And I was able to design a couple different sense-based activities that K through 12 teachers could implement in their classrooms if they so wished, and I'll be presenting that at the AAPT meeting this summer. So my demonstrations revolve around these questions. How does light travel? What does sound look like? How does energy smell? What does friction feel like? And how does matter taste? The first one kind of reflects the last demo that I did with the sock. And it's just this idea that kids can play around with mirrors and move light around the room. And I just wanted to mention all of these lessons are based on the next generation science standards. They each connect with a different standard. And so all of these lessons directly can be implemented into classrooms and meet those criteria that a lot of teachers have to complete in their school years. So we have essentially a laser, a couple mirrors, and you get to play with light around a room. For sound, this one I'm particularly proud of. It's called an Edophone. And the first Edophone was developed in the 19th century by an opera singer. But it's a cup where you stretch a balloon around it, stick a little cardboard tube, and you sing in it. And this is a very poor video, but I was recording it and singing into it. You can observe interference patterns of your voice on the top. So where your voice is the loudest on the cup and where it's the waves of your voice aren't moving very much. The third one I have is smell. This one's also kind of complex, but when you have a hot cup of coffee versus a cold cup of coffee, which one do you smell more? Hot. And that tells us something about the energy associated to the cup because when you have a hot drink, it has more thermal energy than a cold drink, and those particles in the hot drink have enough energy to pop out of that beverage and into the air. So this demonstration involves taking hot chocolate, mixing it with hot water versus cold water, and seeing which one smells more. Why do we know that that one has more energy? The fourth one is friction, and the kids that I watch, they love playing with cars, and they intuitively know that the car is going to go faster on the hardwood versus the carpet. And it's all about feeling different surfaces and guessing which one is going to go, which surface is the car going to go faster on. Last is taste. It's a very fun one. The melting and freezing of ice cream deals with the states of matter. And then if you leave the cup out long enough, it'll form condensation on the outside. So you have a couple different phase transitions there. But one thing I really want to touch on is why is physics outreach and education really important? Three things that I've been reflecting on this summer are building trust in science, establishing good associations with young children, and knowing how to ask the right questions. This is really important that we introduce physics to not only the young people of our generation, but also to the general public. I think that the more people interact with physics, like demonstrations, the more comfortable they'll become and the more trust they'll have in it. If we teach people at a young age how to ask the right questions about science, they won't be skeptical of it later in life. We need to be able to teach people how to ask the right questions so they build those bonds and trust in the future. I want to say thank you to my mentors, Justine and Michaela. This has been a wonderful summer, and I've learned so much. And I'm excited to become a physics educator. Thank you.
Thank you, Naomi. Any questions?
Hey, good job, Naomi. Thank you so much for that. I was just wondering, you said the socks were intended for like K through 12, but that's kind of a really broad range of knowledge and math and stuff. So did you kind of develop different instructions based on what age it's targeted at, or were certain demonstrations for different ages? Or like how did you kind of tackle those differences?
That's a very good question. So each demonstration is made to it's capable for a young child to complete. Young children can physically do something, but then I've tailored each of my write-ups to the specific age range. So we have an age range from K through elementary school, and then we have a middle school age range, general public, and then high school. So each of the demonstrations has an in-depth explanation depending on who is doing the demonstration. So,
thank you.
Thank you for that. I'm glad to see you doing this work. I'm glad at the end you mentioned making the right associations and helping them kind of understand that context. How important do you also find to give them the right vocabulary to start introducing science words that they understand what those mean?
Yeah. So in each of the demonstrations also, we highlight a lot of keywords, those words that we say like friction, force, magnetism, which is a big word for some kids. But we do highlight each of those sections has a keyword section where those are things that you talk about as you're doing the demonstrations. And they're meant for college students, by the way. College students are putting on these demonstrations with these people, so they should have an understanding that they can relate to younger children.
Awesome. Thank you, Naomi.
Yeah.
Okay. Next, we have our intern from Lawrence Livermore National Lab, Riley.
Hi, so I'm Riley, and this summer I've been working on a project called NOVA with Dr. Dave Rakeshaw. Hi, Dave. The question we're tackling is how can generative AI and smartphone sensors make labs more engaging, accessible, and conceptually meaningful for students. So, physics labs are meant to connect physics theory to real-world data, but there are often barriers that we run into. So for one, instructors, especially in large or under-resourced classes, don't have time to give every student the one-on-one attention that they may need. And often students get stuck with technical barriers like Excel or Google Sheets before they can even begin to analyze their data. Students also struggle to see how their experiments connect to physics concepts that they're learning in class, which can often lead to disengagement. So many students leave labs feeling more confused than curious, which is not good. So to kind of get started on this project, we went on a little AI deep dive. So we uploaded raw sensors into GPT-based models. We specifically focused on ChatGPT 4.0 because it was the most compatible with the files that we were uploading. And we designed prompts to see kind of what AI could actually do. So could it explain concepts, perform calculations, and interpret graphs? And the answer was yes, but kind of to an extent. So when prompts were clear and it could filter out noise, smooth data, and even explain patterns in the data to students, which was very good. We also experimented with creating custom GPTs. So on ChatGPT, you can make a custom GPT where you upload a file and then give it specific directions and have AI interact with you in a certain way. And so, for example, we had a version of a lab where Spider-Man was conducting it. And it was a rubber band friction lab to test different personalities in guiding students, which was just kind of interesting. And this deep dive kind of showed us that AI isn't just a calculator or a text generator. It can also act as a learning partner and makes labs both more clear and engaging for students. So this is where Nova comes in. Nova is, in theory, a generative AI assistant designed to act as a lab co-investigator. And it would integrate directly with your smartphone sensor apps like Firefox or Physics Toolbox, which a lot of physics educators already have and use in class. And it would help students analyze their data in real time. So kind of how it would work is a student would launch an experiment from a curated lab library in the app. And then Nova would guide them through setup, calibration, some pre-lab questions, make sure they're familiar with what they're doing. And then as data streams in, graphs are generated live, and you can kind of ask Nova about trends and peaks and slopes and just information about the data. And then Nova would use a Socratic method. So instead of giving direct answers or just kind of giving students answers, basically, it would ask guiding questions like, what could this peak represent, or why do you think that the slope is changing here, for example? And kind of the main goal of Nova would be to automate repetitive tasks. So when you're doing things like peak detection or smoothing, it can be very tedious to use Excel or go in by hand and do the step over and over and over again. So once a student shows basic understanding and can do it once, there's no need to be doing it 10 times or 20 times. So it would automate that. So it's to shift student effort away from tedious calculations and towards higher level reasoning and reflection. So to test this idea, we designed a lab using a familiar toy, the fidget spinner, which I'm sure a lot of teachers love the fidget spinner. But we were able to test this with 30 high school students. I was able to visit the Lawrence Livermore lab this summer while Dr. Rakeshaw was conducting a STEM with Phones workshop for 30 high school students. So we tested it, and we had the students attach a small magnet to one arm of a fidget spinner, and then they placed it near their phone's magnetometer. And then using the Firefox app, which is just a sensor app, they recorded magnetic field data over 60 seconds and were able to capture rotations. So the raw signal looks like an oscillating wave, but it gradually stretches out as the spinner loses speed. So we took, you can see the gradual decrease. But so first we had students manually calculate what the angular velocity of the fidget spinner would be by picking different points in the data, so at like 10 seconds, 20 seconds, 30 seconds, and then kind of draw out what that graph would look like. But in doing this, they realized very quickly that it would be, for all of these data points, it would be easier if this was like an automated thing. So we had them upload it to ChatGPT, and we had them plot the raw data, and then we zoomed in on 1 second clips at the beginning, middle, and end, so you can see the beginning, middle, and end, and see how the oscillations changed. And then we asked ChatGPT to find peaks in the data to then calculate angular velocity using the period. But AI's first attempt was a bit wonky, as you can see. It misidentified some peaks and just completely missed others, so it came out jagged and unrealistic. But this was a very good teachable moment for the students because students realized that they needed to refine their prompts once they And once they did this and added constraints, the result was much more accurate, as you can see the resulting graph. So what's powerful here is that none of the 30 high school students had ever used AI for data analysis before, and by the end of it, all of them were having their own conversations with it, manipulating the data in ways that they thought would be interesting or seeing what they could do with it. This lab shows how AI can act as, like I said, more than just a text generator. It can be a partner in scientific exploration if used correctly. It allows students to get immediate visualization, conversational feedback, and a chance to practice their own experimental judgment. So kind of what's next for NOVA would be bringing together the best parts of all of the tools kind of you see in this image. So the rich data collection of PhyPhox and Physics Toolbox, and the accessibility of the Lawrence Livermore Physics with Phones website, and the conversational analysis of tools like ChatGPT, and combine them into one seamless platform where students can collect, analyze, and reflect on all of their experiments. So right now, NOVA is still in the brainstorming and kind of early coding phases to see what's possible. But the goal would be for it to become a standard tool in physics labs everywhere. So this is our makeup logo for right now. And then this would kind of be what we would want it to look like, just like an app, an overall app. And long term, we're focusing right now on kind of building a curated lab library, designing classroom pilots with schools, and then ensuring accessibility through options like device loaner programs and offline models. And I'll cut it short for now. But I just want to say thank you, especially to Dr. Raksha. Hi. And then everybody at AIP, SPS, and yes.
Awesome. Thank you so much, Riley. We have time for 2 questions. Okay, I'll just do some sprints.
Thank you. Just curious, good job. Do you see this replacing TI-80? I still have my TI-89 calculator. It was so expensive. I haven't touched it in at least 10 years, but do you see it replacing some of the graphing calculators and maybe even, what was it, Wolfram Alpha was popular when we were in college?
I would say replace is a strong word. I think instead of focusing on is it going to replace it, it needs to be seen as in addition to another tool that students can use. But I feel like going in and saying that it's going to completely replace something isn't. Because some kids are also going to prefer Wolfram Alpha or prefer their calculator. It's just adding in another resource that they can potentially use to better their education. But.
Hi. Very cool. Is there a way to test like traditional learning methods versus the kind of supplemented with AI learning methods to see the type of retention? Or is there any interest in doing that?
I think absolutely yes. That would be something once everything is kind of developed and we have a working thing. It would be very interesting to see the comparison of. So I can see Dave hosts a lot of. He hosts a lot of workshops that work with PhyPhox and just using STEM or using smartphone apps in physics education. But it would be interesting to do 2 separate ones and compare which students enjoyed using NOVA, for example, rather than the original. But in the workshop that we did use where they were using AI, it was you could see the kids, they really enjoyed it, and they were all very interested in what they were learning. So.
Awesome. Thank you, Riley. Our next presenter is Lena. She is an APS Public Affairs intern.
Oh, amazing. Okay, yes, thank you. So again, to reintroduce myself, my name is Lena McRoberts. I use she, they pronouns. I am a rising junior at Pomona College, double majoring in physics, studying astrophysics, and gender and women's studies. And I'm very excited to talk to you today about science for the people, designing tools for public engagement and federal lobbying. So as we can see here from the Pew Research Center,
public trust in science has declined significantly since the pandemic. We have an increased fear of, vaccines somehow causing autism, or the idea that raw milk is somehow more pure than pasteurized. But we also have things like the increased fear of the surveillance state and biopolitics, and the development of military weapons somehow being used to expand U.S. empire. And yes, some of these fears are unfounded and based in disinformation, yet all of these fears really point to distrust in systems and in institutions that feel remote and unresponsive and unsafe. And so the challenge that I had this summer was not to simply correct misinformation, but was really to reckon with the structural reasons why people feel so alienated from science in the first place and attempt to change that. So, no pressure. So, first, I want to talk about what a friend and I somewhat crudely referred to as changing the culture. How do you begin to shift a relationship where one side feels unheard, namely members of the public, and the other side perhaps above the conversation? A lot of the time that is scientists. Well, one thing that you can do is you can do it with deliberate, slow, and reciprocal dialogue. One of the really unique strengths of the American Physical Society is its national outreach, right? We have members that span universities and national laboratories, and we thought, we began to ask, what if each of these APS communities led on-the-ground engagement by hosting their own dialogue-based events, bringing together their respective scientists and members of the public, so that being teachers and parents and indigenous scholars and environmental activists and anyone who just feels distrustful or uncertain of science, and invite them into a meaningful conversation. Yes, the work will be slow and oftentimes unglamorous, but also deeply local and grassroots in nature. After all, this is how culture shifts over time. And so after researching a range of dialogue-based events and also collaborating with Princeton University's Plasma Physics Department, as well as the Science Education Department, I have what you see today, which is, and what Rosie will pass around too, the more tangible version of it, which is a public dialogue toolkit designed to help APS units facilitate structured conversation to rebuild trust through dialogue, fostering mutual learning for both the scientists and members of the public. So just briefly I'll go over a few things that are in this toolkit. You see here we have the table of contents. What is it? Why do it? The main section is this big facilitation guide. And then over here we have tools and materials adapting to your own local context. We also have prompts, again, highlighted here, things like what role should science play in your life or not play? We also have visual participatory tools. One of my favorites are these prompt walls. So you can sort of imagine putting butcher paper on 3 walls and having these prompts, and participants can go up and respond to the prompts and see how their ideas are changing throughout the event. And then we also have, really importantly, this section on adapting to your local context. And that's really understanding that trust building is going to look different across every community. The toolkit also includes a QR code, so you can see that has access to signage and prompts. And then something really exciting is we're actually going to be piloting this version here in the DC office next week. So we're going to be bringing together 3 to 5 local scientists and 3 to 5 public members, sort of testing this out and hearing what worked, what didn't, and what needs to improve before national rollout. So it's very exciting. But alongside this community-centered work, I also was able to connect with APS's government affairs team to work on a broader initiative focused on federal advocacy, specifically how we communicate the public value of science to lawmakers. Our goal was really to develop a visualization tool that could strengthen the government affairs lobbying efforts by clearly illustrating the long-term public value of federal investment in scientific research. What we ended up creating is a tech tree. So as you can see here, this is kind of loosely modeled off a family tree. At the root, you have some fundamental scientific achievement, and then this branches out into these different branch themes as well as leaves. And then these leaves are technological advancements that have been able to have occurred because of this root fundamental scientific achievement. We ended up creating 2 of them. This is an example you see here, which is the atomic clock. I won't go into all the details here, but you can see some really helpful things like, when this happened, where this research was occurring, as well as the federal investment. And I think it's really helpful because, it's really easy to imagine our APS lobbyists walking into a congressional office with this in hand, showing exactly how federal investment in fundamental science leads to technologies that voters use every day. And then lastly, I've also been able to connect with editors at APS News as well as the International Year of Quantum, so two major platforms in the physics community, to write pieces that reflect on the questions that I've been sitting with a lot this summer. Things on science and on trust and on, I think, the conditions that we build knowledge in. The first is an op-ed on the rise of how AI in undergraduate science has sort of reflects, I think, a broader culture of optimization and is really sort of a call to reincorporate the values of, of unknowing and sitting with uncertainty and sort of this prolonged struggle. And then the second is this opinion piece on tracing sort of the history of how we've kept time, eventually sort of landing on the atomic clock as the pinnacle of timekeeping precision, and then reflecting on the remarkable fact that, even amidst geopolitical division, we continue to sustain a shared global commitment to timekeeping. And then I actually wanted to end by reading a section from a poem by a wonderful poem by this author, one of my favorite authors, Alison Lutterman. It was published in The Sun in December 2006, and I'll read part of it, but the title of it goes, "Saddam Hussein is writing poetry in solitary confinement." And so it goes, "Forget Saddam. Imagine for one moment all of the work-roughened hands that have picked your food and sewn your clothes and kept you alive since day one. When we die, will there be a reckoning of what and whom we've used to pay for our lives, and how and will lack of imagination be used as an excuse?" And with that, I want to thank my wonderful mentors, especially Ali, Claudia, Nico, Taryn, and Alexandra. Thank you so much.
Thank you. We have time for a couple questions. I see one over here.
So thank you for the presentation. That was awesome. My question is, for those sort of scientist and public workshops or dialogue sessions, I guess, for example, for the one next week, how do you find members of the public to participate in these? Who are they specifically?
Yeah, that's a really great question. So one of the things that we're doing, I guess, for our event here is we made a flyer, and we've been using sort of our local outreach with people in sort of science to be hey, I guess people at APS being you work at APS, but you're also involved in your local parent, teacher-parent group. You're also do yoga. Maybe you could sort of send this out to people that you're involved with. We also have done things through churches as well as just build office buildings, and we also have put out an Eventbrite. And so we sort of see scientists reaching out to their community through their own connections, and then as well as sort of these local communities in their own broader community. Yeah.
Awesome. Any other questions?
I can just project.
Yeah, just project.
I'm just curious, building off of that, when you're advertising this, I'm curious how you make sure you're reaching people who are more kind of hesitant about science. Because I'd imagine if I was I hate science, I'm an anti-vaxxer, blah, 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 and I get an EP, American Physical Society thing, I'm gonna throw it in the trash. So I was wondering if y'all have any strategies for kind of combating that initial resistance to it.
Yeah, that's a really good question. I would say that one of the things that I have done research on is I've looked at actually some interesting organizing spaces that have worked alongside sort of religious scholars in the context of alongside, I think, groups that have been, I guess, more hesitant for science. And I think what we should be doing, what we hopefully will be doing, is I think sort of looking into and I guess encouraging our SPS sites and chapters to be, I think, strengthening relationships with those sort of maybe groups that are potentially more hesitant of science to I would say, spread the word. But I think that's a very valid concern. It's a concern that I've also had. So yeah, thank you.
Awesome. Thank you, Lena. All right, we have our next presenter, Rosie, our APS Public Engagement and Step Up intern.
Hi, like Kayla said, I'm Rosie Derland. I've worked with APS Public Engagement on a few different projects, mostly Step Up and Physics Quest, which I'll talk about. But yeah, I focused on a lot from entanglement to engagement, and I want to talk about what I did this summer. So my two main projects were with Physics Quest and Step Up. So with Physics Quest, I was working on direct pedagogical materials going into classrooms. So lesson plans, I was doing research on quantum topics. And for Step Up, I was focused on career profiles, conducting interviews with people, and doing some research. And I'll get more into what that looked like. So what is Physics Quest? Let's do a little bit of background here. So Physics Quest is a long-standing APS public engagement initiative, and they publish 4 activity-based lesson plans every single year that are focused around one topic. So 2024, it was about plasma, and 2023, it was about waves, and we always try and connect it to a real living scientist and their story with that kind of science to kind of humanize science. So these lesson plans are made freely available to middle school and high school teachers every year. So this year, is the International Year of Quantum. I don't know if you guys are aware. It's designated by the United Nations as the International Year of Quantum to celebrate 100 years of quantum science. So Physics Quest is partnering with that to create 8 instead of 4, activity-based lesson plans focused on quantum physics for middle school and high schools. Now, the challenge is quantum physics is really hard. So a lot of teachers actually lack a background in quantum physics. AIP estimates that only 35% of high school physics teachers have a degree in physics or physics education. And of course, for middle school teachers, this is going to be much lower. So my challenge was to modify 8 existing lesson plans to make sure that they were completely accessible to teachers without a quantum background and, of course, their students. I wanted to make sure that you could flow seamlessly in between these lesson plans regardless of how many you wanted to implement, and that they were really pedagogically sound. So what did this look like? I ended up doing a lot of personal research on quantum topics. I have not actually taken advanced quantum yet, so I was the perfect target audience for this. I wanted to make sure that I could understand what this lesson plan was and then be able to teach it to somebody else. This involved a lot of putting on the teacher hat, putting on the student hat, looking through these lessons and being like, what's missing? Are there any gaps here? And I ended up modifying a lot of explanations to make them as simple as possible while maintaining completeness. So I realized while looking through these that several of the lessons were about quantum computing, which was so cool, but we didn't actually have a lesson about quantum concepts in the context of the atom and just the electron. So I decided to fill that gap and create a prequel to Activity 4. And so in this prequel activity, it can be a standalone activity or it can be condensed, and it uses dice as an analogy for electrons in an atom and for superposition. So you can imagine when you're rolling dice, when you haven't rolled it yet, you don't know yet what you're going to measure until the roll is complete, and then the measurement is decided. So what students do is they roll a pair of dice 30 times to create a sample distribution, like this one that I created with my mentor. It's a real random sample distribution. And so you can talk to students about how we may not know exactly what each sum is going to be, right? Because we're summing the total of these 2 dice every time that we roll it. But after a while, a pattern starts to emerge. And this is true for detecting electrons in an atom as well, as far as where they will show up in the atom. So the next thing that we do with students is we actually have them visualize this probability with a color spectrum. So students get to pick their own color spectrum and then transfer that onto this sum sample distribution. Now, why would color be helpful in this context? So color-coded data is actually really useful for things that we want to be able to talk about spatially. So we're really used to color-coded data for things like weather or topographic maps, right? Now, the atom is a spatial thing, and electrons have a spatial probability distribution. So what students do, with this right here, in case anyone isn't aware, is a spatial probability density diagram for an electron. So each of these dots represents when you detected an electron, where it showed up. And you can kind of see they cluster together in certain areas and then are a little less dense in some other areas, right? So by the end of this lesson, students are picking one of these images and then on a blank paper using their color key that they came up with to turn it into a colorful probability distribution. And this gets students used to seeing charts like this, which come up a lot later if you ever want to look into the electron and learning about the quantum model of the atom. So after I finished up that prequel lesson, which was so fun, I went back and made sure that the remaining lessons were all very clear and concise and made sure that they all matched the APS style guideline requirements. And I unified the structure of all of them so that if a teacher implements one lesson, then they know what to expect for all of the rest of the lessons. It makes it more accessible. So that was the first part of my summer. Second part of my summer, I worked more with Step Up. So Step Up is a community of educators, researchers, and professional societies. And the explicit goal of Step Up is to increase the number of women and other underrepresented groups majoring in physics at the collegiate level. And we realized we needed to actually do work in high schools earlier on to make that possible. So we do this with a few different educational materials. One of those is the Careers in Physics lesson. So the Careers in Physics lesson is beautifully simple. Students take a 2-question survey. The first question is, what are your interests? And they select a few. And the second question is, what do you value in a job, like having time with family, making money, things like that. And then they end up getting matched up with profiles of real scientists who majored in physics that are now doing things related to this student's interests. So my challenge was that the Careers in Physics profiles needed a little bit of expanding. So we wanted to include more types of science communication, maybe more industry professionals, and more musicians. We thought that would be kind of fun. So my job was to reach out to possible interviewees, do some background research, and produce some profiles. So I ended up producing 2 profiles. The first was for Shama Wegsman, who's the podcast host of Why This Universe. It's a physics podcast, it's really awesome, and a freelance science journalist. So I got to reach out to her and interview her, and it was really interesting to hear about her journey in physics and coming to where she is at with science journalism now. And then, some of you may know, Brian May, rock guitarist for Queen, is actually a PhD astrophysicist as well. And so I unfortunately did not personally interview Brian May, but I did do research about his background and reached out to his team to see if we could include his profile in our Careers in Physics lesson. So it was also really interesting to learn more about his physics background and what that looked like and how he ended up returning to physics even after all of this stardom because it was such a passion for him. So I learned a lot in this internship. For Physics Quest, I learned that creating activity-based lesson plans takes a lot of planning. This was a project that was not supposed to take very much of the summer, but we just realized how much these actually needed modifying in order to make them really accessible. And one of my favorite things that I learned is that you can teach quantum concepts as early as middle school. I was blown away by some of these activities that our collaborators had come up with because of how simple they are and how effective they are. And also I just learned about myself that I actually really enjoy, like unifying documents and doing copy edit type stuff. That was news to me. I was like, oh, this is kind of fun. And then also with Step Up, I loved learning how many amazing things people who study physics can do. And I feel like I was getting the Careers in Physics lesson while I was making more of it. It was amazing. And I just also really enjoyed the human aspect of hearing about people's journeys through science. That's a really important thing to me. And I just want to be a high school physics teacher now more than ever. Also, very, very special thank you to my mentor, Nicole Schrody, best mentor anyone could ever ask for.
Thank you. We have time for one question.
I like what you did. It's very impressive. I already told you I liked it, but do you think your work can be expanded beyond this to other topics within physics or no?
Like Physics Quest?
Yeah.
Yeah, I mean, we try and do a new topic every year. So next year, I think it's going to be climate. And so, yeah, we're going to try and tackle as many as possible where we make the lesson plans available to teachers. Does that answer your question?
Yeah.
Okay.
Good job. I liked it.
Thank you.
Awesome. Next up, we have our U.S. Geological Survey Research Intern, Kevin.
Thank you. So, my name is Kevin. I'm from BYU, Idaho, as you can see on the intro. And I have been working with Dr. Hackley for this summer at USGS, messing around with the microscope that they have new arrived. So, with using the sedimentary rock samples that they have provided for the summer. So, the reason why that we're doing this is that USGS has periodically providing oil and gas assessment around the region in the United States and globally. As you can see on the graph here, that we have like the green and red dots throughout the map, and it's telling you that, yeah, this is a place that you can look for oil and gas assessment. And by doing that, on the program for the Energy Resource Program, they have laid out different methods of how we measure where to assess these resources in the United States. So part of my job is to use a newly arrival microscope. This is the fluorescent microscope that it uses the UV lights or blue lights to shoot on the sample on the stage here, which is this is a sample that we have when we sample with the organic material. This is the organic material that the blue light shooting on and get excited and reflect the fluorescent light. And we use a spectrometer here to collect the spectrum to identify this spectral peak to measure the redshift on the spectrum with different sedimentary rock samples. And from there, we draw a baseline to see where the boundaries that you're good for taking out for the oil and gas, and where it's like, no, this is not ready yet, and you should not go and look for the resources. So because the instrument is newly arrived, and there's no standard operating procedure, so we're in the dark. Okay, we have a manual, but what were you doing with that? And we need to standardize it. So part of my job for the internship for the summer is to mess around with the instrument by not breaking it. And my objective here is kind of short, but I have laid out a lot of different tests. But I focus on the instrument preparation time, calibration conditions, and number of measurements that I have. So going into the instrument preparation time, so I do a lot of tests for calibration using the calibration lamp by letting the instrument to have like heating time. So what if I take the calibration right immediately, I turn it on the instrument, how it respond, and let it set 5, 10, 15, or 30 minutes. How it respond to the instrument. So on the left over here, that we have a calibration spectrum with different heating time for the instrument. And as a result, we can see the spectrum structure is laying out very consistently, which is we're happy to see that, because if it's changing a lot, then it would not be a good news. But we realize that we have a different signal intensity here that we're questioning, is that correlated with the time heating on the instrument, or is this the spectrometer have different sensitivity each and every day? So on the graph over here on the right, we let the instrument set for heating up for 5 minutes every single day, and we take the calibration and put it together to see what's going on. So as a result, we can see that the signal intensity is still changing, and we can conclude that calibration has to be done every single day, because the spectrometer just have different behavior every day. So today may be a little bit happier, so I'll give you a different spectrum, and then the day is like, no, I'm not happy. So, but throughout that, we have a conclusion that the instrument heating time has no correlation to the calibration and process and data collection. However, we still seek for the very secure stability for the instrument. So we following the suggestion by the manual that saying letting instrument heating for 5 minutes will be producing the best performance. So we're following that advice. So this is the calibration condition. So because we're taking the sample in the laboratory environment, so what if we switch off the light and we switch on the light, or what happened to the instrument during the collection? So this is a microscope. I zoom in really big, and this is a calibration lamp that we have here, and then objective here, and a cardboard I place on it to see the response. However, matter of fact, I almost break the instrument by doing this. We do the calibration, letting the copper placement on and letting it heat up for 5 minutes, 10 minutes with the lights on. And then what if I take away the cardboard, and then I switch off the light, place back the cardboard, and then I take away the cardboard when the light is off, and then we see the response to calibration. So this is the graph that we have. By taking the calibration, everything looks fine except one line. If you can pick up, the green line is having a little bit more bumps. That's where we don't want to see. So, and as a result, we see that when the lights is turned on without the cardboard, we have a lot more interference with the environmental light. So as a conclusion, we conclude that we have to do that calibration during the dark and taking our data collection in the dark. So it could be for hours, so don't fall asleep. So we also want to optimize the number of measurements in the sample we taken to minimize the time that we taking measurement for every single samples, because once the standard operating procedure lays out, we have a lot of requests on doing the samples, so we don't want to take like hours for one samples, but optimizing the number of measurements that we have. So we're using the coefficient of variation, which is, I call it CV values, which is using the standard deviation divided by the mean. So it's telling us that how much it changes in the matter. So our goal is to let the CV values stay 0.1 or relatively lower than 0.1, which is pretty high stability. It's not changing a lot, with the standard deviation of the CV values relatively low. So I have laid out different tests here. That A here is 7 co-samples that we have, and then I just keep taking different number of measurements, and then in 100 micrometer diameter that we have for the spectrometer, and then I use 200 micrometer cable for the spectrometer on sample B with the same 7 co-samples. C and D is 2 show samples in 6 different environmental conditions. So by putting it together, we can see that 10 measurement is having a relatively stay within a bounds of 0.1 CV values, with the relatively lowest standard deviation for the CV value. So we're going to stick with 10 measurements. It's good enough to accurate for our measurements. So as an outcome for me, I have laid out like many different tests, but I just show part of it for my messing around the instrument. But I have developed this standard operating procedure for peer review to be used for USGS. At the same time, also we prepare for a paper for published for the worldwide collaborator using the instrument fluorescent microscope, that we have a standardized procedure that we have data that we can put together for calibration in the future. So lastly, I want to acknowledge that AIP and SPS gave me this opportunity for me to work with Dr. Hackley at USUS, and my colleagues have been helping me at USUS for this project. So thank you for your attention.
Awesome, thank you. We have time for 2 questions. Behind me. We'll go here first since I'm right here. You guys in front.
What was the coolest thing you saw under the microscope?
The coolest thing that I saw under the microscope is actually there's a lot of minerals that it actually really excited when you shoot on the fluorescent light on it, and it just there are times that my eyes almost got blind in the dark because it's too bright. But yeah, I'm very excited. But also, organic material is really, really cool because I never realized that if you zoom into the samples, like those organic material is like 63 times maximized. So when you're grinding the rock to make a sample, you never think that the organic material is in there. So it's really cool. Yeah.
Oh, yeah. Thank you, Kevin. I was just curious, in addition to your great work that you did for all these different things, how much of the procedure did you have to adjust based on when you almost broke the microscope?
Okay, so actually, I got really lucky because we go through the procedure, we shut down the microscope because it screamed at me when I was breaking it. And then we let it set for 20 minutes, and then we decided to say a prayer that please just fix itself. And as a matter of fact, that it does really fix itself, and then I don't have to do additional work for adjustment, so I got really lucky from it.
Awesome, thank you, Kevin.
Thank you.
Awesome. We have our FYI intern, who is also a second-time intern, Jenna. So give us a round of applause.
Come back. Can you hear me okay on the mic?
Yes.
Okay. Okay. Hi, everyone. My name is Jenna, and I'm this year's FYI Science Policy News intern. And I'm going to be the bearer of bad news, no pun intended. Laugh, please. Thank you. Okay. But I'm going to be talking about the federal budget system and how FYI tracks the federal budgets, especially in these uncertain times. So before I begin, I just want to go over what we're going to talk about today. So we're going to go over the budget system, obviously why we care, and then we'll go into the budget tracker. So the early stages of the budget starts with federal agencies like the Department of Energy, Department of Defense, Department of Commerce, so on. They create internal budgets based off of their own office requirements, and these agencies each submit their proposed budgets to the White House Office of Management and Budget, or OMB, in the early fall. So the budget process actually happens what's during it called a fiscal year. So the fiscal year starts on October 1st and then ends on September 30th of the following year. So technically right now we are budgeting for well, not me, but the government is budgeting for FY26. So that would start at the beginning of this October and then end in September on the 30th. So we budget a whole year ahead of time. So OMB then reviews the budget with the agencies and negotiates with them in alignment with the president's policies. And then compile the president's unified budget proposal and a discretionary funding request. And so this is just an example of one. I picked artificial intelligence and quantum because we're all physics here, so might as well. The president submits the budget to Congress no later than the first Monday in February. However, this is not the case, like, ever. But that's just the way the government works. Not NIST. They're great. Gotta say that. Go NIST. This year, the budget was submitted in early May, so just make that note. So once Congress gets the budget, it's divided among 12 appropriations subcommittees in each chamber, so 12 in the House and 12 in the Senate, and each committee holds hearings and markups to discuss further funding and eventually drafts a budget resolution. So the House and Senate must agree on total spending, so they compile, my goodness, one number that they send back to the president. So Congress passes these 12 individual bills, and then, like every other bill, the president can either sign them into law or he can veto them. So this is just an example of what all that paperwork looks like. It's a lot, but this is the president's discretionary request by major agencies. So I'm just going to be using NASA as an example, because again, we're all physics in here. Why not? So each agency also releases their own total request summary that outlines spending in each program. This is a little bit more detailed. You can see that something like the International Space Station is labeled out, and that's not the case in most other documents. The House and Senate then draw up their subcommittee markups. So this is an example of the House subcommittee for NASA's budget, and they only highlight the top numbers in each program. And then the House and Senate will also release their full appropriations committee. This is an example of the Senate's appropriations committee for NASA as well, and it also highlights the top numbers. So you can see this is the top number that the Senate is requesting or recommending for FY 2026. So why are we here? You can see, obviously, there's a lot of news, a lot of spending. Oops, my bad. So it's no secret that STEM is getting hit pretty hard when it comes to federal funding. I think we're all in the know of that and all have opinions on it. I probably have the same one. But despite the budget changes being a major reason for tracking the numbers, the government and other news outlets don't do the best job of spreading the top line science numbers. So agencies like NIST and NOAA fall into the Department of Commerce, and for them it's difficult to kind of find the right numbers for each office and program, especially if people want to know that information. And so collecting more detailed numbers in one can be a game changer for industry, universities, and even policymakers to know where that money's going to. So to combat all of this, FYI has so graciously compiled all of those numbers into one area called the Budget Tracker. This tracker dates back to the fiscal year of 2017, and it provides up-to-date information on appropriations, proposals, resolutions for each agency that fund the physical sciences. So how FYI compiles all these numbers is a pretty extensive process, especially when you're sitting on a train trying to collect numbers and the budget only goes one way and it's horizontal, or it's vertical, and you got to flip it horizontal and everybody's staring at you. Anyways, FYI collects these numbers from the initial request, the House and Senate subcommittees, and the House and Senate Appropriations Committee, and they keep track of top-line programs such as human exploration, science, again we're going with the NASA theme. But FYI also keeps tabs on things like that are considered basic research, applied research, and more depending on the different departments. So we collect these numbers once they're released, and we compare them to the prior year. So in this case, we're comparing it to FY 2025, and we track the percent changes according to the request, Senate, and House. So for human exploration, as an example, the House is requesting an almost 30% increase than last year's final number. So it also just helps to see that in some cases, like the Senate might be pushing back on the president's request a little bit for funding, or the House might be pushing back also on funding, kind of going against what the president's policies are. So FYI also compares the top line numbers for each program to what they were in previous years, dating all the way back to 2017. And then selected programs that we follow in each agency are also shown again with percent changes, but with just a sub-program detail. So another main reason why FYI tracks budget numbers in detail is because of the stories that they can tell. So simple numbers can lead to stories about budget cuts, congressional hearings, workplace environment, and so much more. And these articles are FYI specific, and they're broad stories with snapshots of random moments in which a budget develops. So for example, the article that I so graciously published was on the nomination of Neil Jacobs to be the administrator of NOAA. And so NOAA has been on the chopping block when it comes to federal funding. And a simple nomination hearing turned into a huge budget debate with Neil Jacobs stating that he supports the president's 27% budget cut, but then stated, in quotes, "I don't know that you could spend too much on research." A little controversial, but okay. So this summer, I also had the opportunity to help with the weekly newsletter that FYI sends out every Monday, and I helped collect a ton of numbers across multiple agencies. And so all these tasks in some way or another related to tracking budgets. So the main gist I want to get out is tracking these numbers is really crucial, especially in these uncertain times where we don't know what's happening. So I would like to thank my wonderful mentor, Jacob. Everybody clap for him. Yay! As well as Mitch and Claire on the FYI team, Michaela, Kayla, the SPS Interns, AIP, SPS, and so graciously to High Point University for giving me a degree. Shout out to them. So I'd be happy to take any questions.
Thank you so much, Jenna. We have time for 2 questions.
What was your favorite experience during your time working?
I really enjoyed going to the Hill, especially for the nomination hearing of Neil Jacobs. That was an interesting hearing. Definitely, I think that was the highlight. And then publishing my article, of course. Shout out to that. So.
Awesome. We have one more question.
What role does physics policy play in your future, either in terms of going into it or in terms of using it in research?
Hannah, I hate that you're asking about the future.
bad.
I really enjoyed working in policy. Again, this is my 2nd year doing the internship, and I did policy in both this year and last year. And I really do want to continue it. I've talked to some people on the Hill, like who work on the Hill, about what it would look like if I were to work on the Hill, and like what science policy looks like in that case. Or just trying to work for like another federal agency, I think would be very cool. But I do want to continue going down that path. Maybe somebody hire me, please. But yeah, so there's that question.
Thank you, Jenna. Our next presenter is James, our SPS Careers Toolbox intern.
Good afternoon, everybody. As Kayla said, I am the Careers Toolbox intern. My project title for this summer was Tools with Purpose, Modernizing the SPS Careers Toolbox to Better Serve Today's Physics Students. So before we get started, I do want to give a little agenda about what we'll be going over today. So we're going to talk about what is the Careers Toolbox, my story/connection with others, project goals, the advisor survey, design strategy, future goals, progress so far, and my takeaways from the internship. So there was a problem, and we needed a solution, right? So a lot of physics majors go to school. They don't know what they want to pursue. Some of them don't want to go to grad school. Some do want to go to grad school. But it was the lack of career preparedness that physics students got. So in order to combat this, AIP decided to come up with the Careers Toolbox. And it was made to equip the physics students with tools that they could use to find a career later on in life and to be prepared. So this right here, when I first arrived, this was all the data that we really had on the Careers Toolbox was this spreadsheet. I decided to put it onto a log scale. Thank you, MJ. So you guys can actually see what's actually going on here. But I decided to highlight there were 250 uses as course material, 280 uses for personal purposes, and 106 uses for mentorship. And the problem with this is that because at the time when Careers Toolbox was created, there wasn't a lot of faculty and resources dedicated to the Careers Toolbox to properly advertise it and to track the data on it. So that was, I guess, a problem or an issue. Yeah. So the reason why I decided to include this part is because I'm just an intern. You know, I came in with my opinions, my thoughts, and I got a passion for the project the more I spoke with the people that I work with. So it was trying to turn that passion that I had for the project into these other people that I had to work with. So I think that was another challenge that was there. But luckily, everybody that I worked with was pretty nice, and it was easy to work through it. So it was good. It was good. So I thought it would be smart to divide the project itself up into 4 phases. Phase 1 being gathering input. So we conducted the student focus group survey, then we did the advisory survey. We want to use that feedback to start the migration. Then sadly, right now, we're only into phase 2, where we're analyzing the data, and then we're working on increasing the interactivity of the Careers Toolbox. That's what I spent this last week doing. And then as for phase 3 and phase 4, these won't happen until later within the future. But at that point, hopefully, we'll be able to send out another survey to assess how everybody feels about the current toolbox. Then we'll go from there. And then I suggested using PyMe, I guess something fun, I guess, to use in the business world. I guess like a filter system. We have all these features. We want to use AI, resume help, everything, right? But we don't want to put too much into the toolbox, and it's just a big blob of tools, and we can't find anything. So too much of good is bad, you know? And then I also wanted to voice the students' concerns, or the interns, and highlight the main points, you know, what students wanted, more than basic tips and integrated hub. You know, so instead of having to look far and wide for help, how to make a resume, where to look for jobs, where to find research, can we put it all into one place and make it nice and conform? How should it be improved? Added storytelling. I know that was said in the beginning of this symposium. And, you know, show the use of AI that it could be used as a tool also, and not just to cheat on homework and stuff. And then lastly, for format and accessibility, I think the biggest gripe that we got from everybody was that 80 pages is way too much. Nobody wants to read 80 pages. But I think a good takeaway from this was that all the information was useful. It's just 80 pages, you know. And then, once again, from the advisory survey, I highlighted the main 4 points that it was voiced during that, was that students faced a lot of challenges, career clarity being the top one, the awareness of the Careers Toolbox. A lot of the people that I spoke with forgot about it or just never used it altogether. And then content gaps, career assessment, and being able to make a competitive resume. A lot of students didn't know how to do that. And then lastly, you know, format and visibility. 80 pages is nasty, so. And then, you know, summary from all that is that we want to be able to equip professors and advisors with a good tool that they can use to help students, provide clarity to students that only want to pursue a bachelor's degree. And then lastly, I do think, I don't know how this will work, but voice to industry what physics majors can do so they actually know what they're hiring and who that person is and what they bring to the table. And then this is my design strategy that I came up with, something very simple. We gather the feedback, we analyze the feedback, draft the design plan, and then lastly, we begin the initial migration. So this right here is what I have in mind for future goals that can be put into the toolbox, you know, working on an interactive experience, including alumni stories, actually being able to track the data better so we can see what we can add later on, what students are focused on and what they want. And then, you know, finding ways to make it inclusive, not just for physics majors, but engineers or anybody within any point in their career journey. That's what I think. And then my key takeaways was cross-disciplinary collaboration, independent project management, human-centered design approach, and data-driven design, being able to turn words and feelings into actual feedback and progress, which I think it's not as hard as it sounds, but I just thought it should be voiced. And then I want to give a special thanks to everybody that is on this list. Every one of these people helped point me in the right direction, caught all my spelling errors, give me good ideas, and all around helped me be here today. And then right now, since I have been working in the DXP system or software, on platform, my bad, I do want to say this is what I've been working on so far. I've only done tools 1 and tool 2. I don't know if Paul is here. I hope he's not upset, but I haven't ran it by him, but this is what I made so far. So I'm trying to work on making it more interactive. That's tool 1. Then we have tool 2 right here. So like I said, it's a lot of work. I'm working on it. We're making it look fun, but we're getting there. I can only do so much. And then I want to say thank you to everybody for showing up today. And if anybody has any questions or comments, you guys have me.
We have time for quick questions. We have one over here.
Great presentation, James. What do you envision to be an ideal career toolbox that could serve the undergraduates?
Oh, man. I would say, like I said, a central hub. That's the point I really like. I really want it to be a place where anybody at any point in their career could come to build a resume, find jobs, REU research, internships, and really to find mentors. I realized that having a good mentor really is what gets the ball rolling. Like, you can look independently. I know I thought I could do a lot of stuff by myself, but I can't. So I feel like being able to find somebody that you can really talk to a lot and bother and actually get advice from is the way to go. So I really think that the toolbox can be used for anybody, and hopefully we can get it to that point. That's my goal. Couldn't do it this summer, but hopefully the torch is passed on to somebody.
So what I saw, one of your last slides had a number of skills that you needed to develop and draw on, like your project management and several other things that went into this project. So yes, this cross-disciplinary collaboration, independent project management, and the like. So if you were to advise undergraduates starting off on their education, what skill would you say is really essential that they develop for the workforce?
I would say communication and being self-driven a lot of the times. Because I really didn't, like I talked with Alejandro and I talked with my other mentors, but a lot of it was me trying to make my own work and him telling me like, I envision this. And then I turned that envision into something tangible. So being self-driven, communication, and being able to get told, this doesn't look good, or I feel like you should change this, or we can just delete this whole paragraph right there. And also keeping in mind that I think the most useful thing that my professor told me is that 90% of the work that you do is going to be useless, and only 10% of that is going to be used. I remember I made a PowerPoint in the beginning, didn't get used at all. And so, I mean, I guess that's what I would say. That's what I would say.
Thank you.
Yeah.
Awesome. Give it up for James. I would like to introduce you. I know
Yeah,
we're
sorry.
rivals and
Sorry,
all,
sorry.
but
I was too pumped.
all right. Well, we have our last but not least, our presenter, our other Mather intern with the National Science Board, Zane.
All right. Okay, so today, for the last 10 minutes of our presentation day, I'm going to be talking about bootstrapping data infrastructure for science policymaking and communication. And I know you guys are as excited as I am to jump into that. But first, I'm going to start with the non-glamorous stuff. So the non-glamorous stuff. So my name is Zane. I'm a rising senior at the University of Michigan, so go blue. I know we got some green in the crowd, so sorry guys. I'm studying physics. I also spend a lot of my time at the campus newspaper. I'm co-editor-in-chief of the Michigan Daily. And this summer I've had the pleasure of being an AIP Mather policy intern with the National Science Board. And for those of you that need a refresher, the National Science Board is a congressionally established board that has sort of this dual mandate to establish the policies of the NSF, which is one of the main funders of science and engineering research and talent, and also sort of be an independent science advisor to Congress and the president. So I wanted to start off to give with a little introduction into science policy, as much as I have the credentials to do so 10 weeks into my science policy career. Because I think to understand what kind of data that we want, what kind of data that we need, what kind of data that we're looking at, it's important to understand kind of where we are, where we're situated within the science policy landscape. So the way that I like to think about the science policy landscape is a collection of actors and incentives. And I think the four that are the most relevant for this talk are the government, the public, educational institutions, higher education, and the private sector. And so each of these actors have things they want to give to the other actors and things they want to get from the other actors. And these are the incentives that sort of make the science and engineering landscape go. And I think specifically it's important to highlight that when we're talking about science policy, when we're answering questions about science policy, when we're making arguments about science policy, it usually has to do with one of these edges or one of these nodes, at least in this science policy landscape. So with that, I just do want to say that is obviously very simplified. But I think it is helpful, sort of as a rule of thumb. You know, there are a lot of stuff that I'm leaving out, scientific societies, philanthropy, and obviously there are like federal agencies that do research, national labs, for example. But I think it's a helpful rule of thumb to sort of situate ourselves for the following conversation. So first, why do we need data? So I think we need data to inform policy, to make any sort of compelling argument you want to have evidence. And we also need data to communicate impacts, right? It's one thing to say, hey, we funded this person, look what they're doing now. And it's another thing to say, we funded X amount of people over X amount of years with X amount of money. But the availability and the quality of data directly impacts our ability to do these things. And so there already is a very broad swath of statistical data that's available in the science engineering landscape, especially by the National Center for Science and Engineering Statistics that's housed within the NSF. And those statistics are good at answering some questions. You know, how many graduate students are in the United States, in what fields, how many people are working in what different fields. But they also are not so good at answering some other questions, especially questions that sort of come up in a dynamic, on-the-fly science policy context. So these are questions that I've encountered in my 10 weeks at the National Science Board that the current federal statistical or just science and engineering statistical landscape wasn't necessarily apt enough to answer. And as you can see, they get on some really important ideas. You know, how good is the NSF at translating scientific ideas into economic benefit? Is NSF an outsized player when it comes to generating new knowledge? And there just wasn't the data infrastructure to really aptly answer these questions. So I want to transition into talking about my work, and I want to talk about 3 data tools that I created with the National Science Board to sort of answer these questions and also more questions. So the first one that I want to talk about is an NSF award search that I made. Basically, NSF keeps track of the awards that it makes, and I downloaded about 400,000 of those awards and wrote a little bit of a Python script to be able to filter through those awards, whatever characteristic that we want, and then also extract whatever characteristic we want from those awards. And so this builds on the current NSF Advanced Award Search, because the current award search is kind of limited by its keyword search. It only searches through parts of the award, not all of it, and it can only return 3,000 awards, which might seem like a lot, but when we're talking about 400,000 over the past 25 years, it actually is pretty limiting. So if we wanted to answer, for example, what does the return on investment look like for AI, NSF company, like AI company seed funding, it's kind of easy with this. Filter the awards by the company seed funding program, define keywords that define AI-related awards, extract those company names and the award amounts, and then you could match those company names to an outside database to find that money they've raised in the following years. So the second one I want to talk about is the index Excel calculator. So right now, the National Science Board and the National Center for Science and Engineering Statistics, or NCSES, are working together to develop a science and engineering index. And this is still under development, but basically what it'll hopefully allow us to do is look over across a variety of statistical indicators and draw sort of a top-line number that'll allow us to sort of easily compare how different countries, how different states are doing in science and engineering. And so what I did was I just made an Excel sheet that's able to calculate an index with, theoretically by using z-score normalization and principal component analysis, which is essentially using eigenvalue decomposition to find the weights, which I didn't know that you could do that in Excel before I did this, but apparently you can. And so basically, hopefully, it allows NSB members and NSB office members to be able to update the data within this Excel sheet and have an automatically calculated index as well. So if you wanted to answer the question, how well is Michigan doing in science engineering compared to Ohio, which I don't know why you would compare those two states. One is clearly much better than the other. But you could theoretically find the index for Michigan and Ohio and just compare it. And I did want to highlight, so all credit goes to Andrew for the conceptualization and the creation of the index. He helped me with making this calculator and stuff, and he's been a great help with it. And I just wanted to highlight these. Obviously, you're not really supposed to read these. The point is that there's a lot of them. And so this index will hopefully be able to allow us to draw conclusions over a variety of indicators. So the last one that I'll talk about is a funding proportion search that basically searches through the OpenAlex library. The OpenAlex library for our cases is basically a collection of publication data and characteristics of those publications that you can see in this diagram. And I wrote a little Python script to be able to query the OpenAlex API, filter through articles with given characteristics, and find who's funding them. So if you wanted to answer the question, what proportion of highly cited US AI and quantum-related articles does NSF fund? You could filter for the articles with those characteristics and then just find the funders. And this builds on current publications data that NCSES uses. They use Scopus, which costs money, and it does have higher quality data, but OpenAlex is much bigger and contains information about funding, for example. So there is information that Scopus doesn't have. So you might be asking, Zane, why did you pick those very specific questions to answer with your data tools? Well, actually, they relate to a test case that came up about 3 weeks ago, and here's the setup. So on Thursday, about 3 weeks ago, multiple conversations with the NSB spurred demand for an NSF AI and quantum fact sheet, and we wanted to make the argument, or answer the question, depending on how you want to look at it. NSF is key to US leadership in AI and quantum, and we needed a rough draft by that Monday so we could send it over to the board, get their feedback, have them revise it. So we needed this draft really fast, and actually having that data infrastructure really helped us answer those questions on the fly, pull that data, and make compelling arguments. So I won't go through it too much, but this is basically OpenAlex data, share of highly cited US AI and quantum-related articles. This is from the award search, is location, award amount, and also follow-on funding by venture capital and anecdotes. This is just regular federal statistical data. This is budget data on the left and NCSES data on the right. And then this is also from the award search, notable PIs, and the notable initiatives as well. So moving forward, I just wanted to say some general proposals for the future. Obviously, we want to make these data tools more robust. Downloading 400,000 awards in JSON file format is not necessarily the most efficient way to do things. And there also are some weird data artifacts with OpenAlex that we'd want to get some more clarity on. Using machine learning to organize databases would be super interesting. There's some notable publications that do the same thing. And then also answering other pressing questions, like how do we fund the next big thing? And using data to do that. So some acknowledgements. Obviously, I want to thank AIP and SPS for their assistance with the entire internship, logistics, placement, programming. They've been a great help with everything. The NSBO staff, they say it takes a village, and I definitely felt like I had a village behind me for all of this. And obviously, my mentor, Amanda, for everything. Without her, I would not be half as successful as I was during this internship. And if I ever am a mentor in the future, I definitely hope to emulate her mentorship. So with that, I will open it up for questions.
That was great. We have time for a couple questions.
Well, I hope you weren't ever bored while you were working in the board office. Did you have any idea that science policy would involve so much programming or physics or those sorts of concepts?
So I didn't, and that was kind of a fun surprise. It was definitely, I think, kind of a characteristic of me being sort of having this technical background in physics and being able to utilize my skills of learning Python and utilizing them and be helpful in the office. So it was definitely a fun surprise, but I definitely think we need more technical capabilities in science policy for sure.
We have a online question.
Go ahead,
Dave. Zane, I was wondering if you tried using AI to do a similar query as you had written the Python code for, and how it worked if you did try it.
For which sort of component?
When you were searching some of the AI related topics before, for example.
Yeah, so actually I did use the ChatGPT deep research function. I gave it a list of company names and saw what it could find to pull out anecdotes. Kind of used it for a glorified kind of Google search. But it actually was really helpful in doing that. So definitely I think there's more capability there. But I guess the thing that we want to keep in mind is it's not super robust. And we do kind of want to find better ways to do it. But it definitely was helpful, and we definitely used it, I would say.
Awesome. Give it up for Zane.
Thank you all. I know we're a little bit over, but a lot better than last year. I would like to introduce Michael Maloney, CEO of AIP, to give some brief closing remarks.
Brief, because everybody's hungry. I know I'm not going to keep you long, but wow. Anyone else share that feeling? Yeah. When I was in this, we were all in this room 10 weeks ago, and we were talking about the experience you're going to have, and there was 3 repeating interns. Did I get that number right? So you knew what you were going to experience to some degree, although I'm sure every year is different. But the other folks were probably going, oh yeah, there's Michael. He's talking about what an amazing experience it's going to be, and these are going to be lifelong friends. And I hope that what we talked about 10 weeks ago, that you've all met your expectations and learned from each other, made lifelong friendships. And most importantly, as somebody mentioned there, how important collaboration, mentorship, friendship, working in a professional environment, how all these things sort of come together to help us do the things that we're passionate about, whether that's working in a lab or in an office or at home, whatever it is that you find your passion in. These are kinds of skills that you'll always be drawing on. And I hope you got some insight into that during the internship. AIP, SPS, we're here to be your partners in your career for the full period of your career and thereafter. We're really leaning into supporting not just the current students that we work with, but also the alumni from SPS and Sigma Pi Sigma going forward. That's going to be a real priority for us as an organization over the next 5 years or so. And also thinking about how to expand on our work with students interested in physics and astronomy, to expand that to students who come from the broader physical sciences community. And that's a big ask for our organization, but something that we're convinced is important. Why? Because as Anna said at the beginning of today's presentations, the physical sciences help shape a better world. And so supporting the future leaders of the physical sciences is just part of our mission. It's what we do. And so thank you so much, but thank you for being around the office. It's been great to have you here. We hope that you'll come and visit again. I want to thank all the mentors and all the folks who hosted interns over the last 10 weeks. In particular, I'm really proud of the fact that we've expanded the set of partners this year to include a whole bunch of new government partners that we've not worked with before. We really appreciate that, especially given that we all know how challenging being in government is right now. We feel for you. We're here to help. So thank you for giving time amongst all that for the students over the last number of weeks. And let's go and have lunch. So thanks very much.